try it just to understand. Very well. Okay. I go in full mode. Okay. Very well, it works. Repeat, sure. Let's wait 2 minutes and we start. Okay, Frank?
Yeah, absolutely.
So guys, I have an announcement. Keep in mind this evening for the social need dinner, you need a ticket, okay?
Oh.
Take the ticket in the registration, okay?
Yes.
And also, if there was some extra ticket, the dinner is here, the floor up, 1 floor up, and 8 o'clock. No ticket, no dinner. Keep in mind. Okay, take the seat, guys. We are going to start. So it's a real pleasure for me introducing Frank Lyman. Frank is a full professor of computer science at the University of Stuttgart, Germany. His research interests include software architecture, robustness and high distributed application, pattern language, and new topic, interesting topic that we are looking for, quantum computing. So Frank will introduce today with us, Ivanish, quantum software help from the cloud. Frank, the floor is yours. Go ahead and thank you.
Thank you very much, Massimo. So the agenda, yeah. So the agenda.
The volume, talk.
Okay. So okay, is it fine? Is the volume good enough?
Yes, you can go ahead.
Okay. So the agenda of my talk today is I will introduce a little bit of quantum computing basics.
Excuse me, Frank.
Yep.
Because we have a 10 device for speakers and I select the wrong one. Go ahead.
So you let me know when I should continue.
You go. It's fine.
It's fine? Okay. So the second subject will be what are the advantages of quantum computing, how to program a quantum computer. And as I will point out, today's devices are still error prone. So and what are the consequences of being error prone? I will introduce the general structure of quantum-based application, which I call hybrid quantum classical applications. I will point out what is the environment, and here I come back what we grid and cloud people can add to quantum computing, how to build such applications, and then I conclude. So a little bit of basics of quantum computing. So the information unit is not a bit in a quantum computer, but it's a qubit, a so-called quantum bit. And this is a quantum gate can be both in the state 0 and in the state 1. Don't be confused about this formula here. It's called the cat notation. We call it cat 0 and cat 1, right? But again, a qubit can be both in state 0 and 1 at the same time. We call this superposition. And so the state, in fact, is not 0 and both 0 and 1, but you have complex numbers here, which are the coefficients here. So it's alpha times 0 plus beta times 1, and this is here the real superposition. So it's a linear combination. Important that the modulus squared of alpha plus the squared modulus of beta is 1. That means a qubit is, so to speak, a unit vector. It's a point on this unit sphere. But you need to take care that alpha and beta are complex numbers, so it's not in a two-dimensional space, but in a four-dimensional space. So in fact, a qubit is something on a three-dimensional sphere in a four-dimensional space. This is hard to comprehend, but there is something that can help us to understand what a qubit is, called the Bloch sphere. Because you can easily prove that each qubit can be rewritten as follows. You find two angles theta and rho, so that cosine theta over 2 times cat 0 plus e to the power of I rho sine theta over 2 times 1. And if you take these angles theta and rho, and you have theta is the angle between the z-axis and the point on the Bloch sphere, and rho is here the angle between the projection of the qubit to the xy plane, then you can basically represent a qubit on this two-dimensional sphere in a three-dimensional space. This is what we can comprehend. We will come back to that. So the intuition behind the qubit is as follows. We know that a bit is 0 or 1, and it has two possible values. It is always in a single values, of course, but a qubit is now something on the Bloch sphere. Any point on the Bloch sphere is a potential state. That means you have an uncountably infinite possible number of values that the qubit can be in, right? And when a quantum algorithm, as will be seen in a couple of minutes, manipulates the qubit, it rotates on the Bloch sphere. But at the end, if you want to read out the result of your quantum algorithm, you need to measure it. And measurement in quantum physics means you destroy the superposition, and at the end you get a 0 or a 1 out of it, but only with a certain probability. So if the qubit is in the state alpha 0 plus beta 1, right, and you measure it, then with probability modulus alpha square, you measure a 0, and with probability modulus beta square, you measure a 1. And after that, the superposition is gone, because the qubit then reveals with this probability whether it's 0 or 1. That means a quantum algorithm is, based on measurement, a random experiment, right? The quantum algorithm does some manipulation in the quantum computer, but at the end you measure a result, and result is only a result. It's not so big. It's a probability distribution that you get out of the quantum computer, and then you need to interpret the probability distribution. We will come back to that. So computation step. Remember that a qubit is a vector of the length 1, and the computation step manipulates the state of the quantum computer, and the result is another state of a vector of length 1. That means a computation step is a linear map that preserves length, and this is what we call a complex unitary linear map, right? It's a linear map in a complex vector space that is length and angle and volume preserving. So it's a matrix, right? And programming a quantum computer, and I will dive deeper into that in a couple of minutes, is linear algebra in complex vector spaces. So as you can bundle bits in a classical computer into a register, you can bundle the qubits, and I represent the qubits here as the Bloch sphere and points on a vectors that have the endpoint on the Bloch sphere, right? You can bundle qubits into a quantum register. That means if you have n bits, right, then you have the potential states is either it's all 0 or it's 0001, 0010, and so on up to 111. That means you have potential 2 to the power of n states of the quantum register. But keep in mind that you have a superposition, a linear combination of these vectors. That is the real state of the quantum computer. They are in superposition. So a quantum computer is always in superposition of 2 to the power of n values. So that basically means a classical register with n bits always has a single value at a time, right? It's the binary number that the classical register does represent. A quantum register with n qubits has 2 to the power of n values at the same time. So if you consider that you have 50 qubits, and 50 is a number that many quantum computers do have today. In fact, we here at IBM, they have 127 qubits, over 400 end of this year, early next year, right? So if you have 50 qubit computers, you have 10 to the power of 15 values at the same time, which is in the order of petabytes, right? That you manipulate at the same time. If you consider 100 qubits, and my group is working with this 127 qubit computer, you have 10 to the power of 30 values at the same time. And in a single step, right, you manipulate 10 to the power of 30 values at the same time. This is what we call quantum parallelism, right? 10 to the power of 30 values manipulated in a single step. This is quantum computer 1 of the origin of the powers of a quantum computer. The next real crazy thing that brings power to the quantum computer is what I explain next. Take a look at this state here. It's a 2-qubit status, right? The 2 qubits are either in state 00 or in 01 with a certain probability, 50%. If I measure the left qubit, I measure a 0, and I destroy the state. But this destruction means, well, okay, the state of the right qubit is still 0 or 1, because if I measure 0, it could be this part of the qubit or this part of the quantum register. So it's always 1, right? That means measuring the first qubit, the left qubit, does not influence the state of the second qubit. It still has the liberty to be in 0 or 1. And the reason is you can rewrite this state as a product. Don't be confused about this tensor product here. It's a product. And if you measure the first qubit, the second qubit has all the liberty to decide for 0 or 1. Here I have another state. It looks quite like this one, but I change 0, 1 here to 1, 1. If I measure now, for example, the left qubit, right, and I measure a 0, then this part is basically gone, right? Because I measured the 0, that means this part of the qubit is no longer available, and the second qubit is known to be in state 0. If I measure a 1, then this part is gone, and the right qubit is known to be in the status 0. That means measuring one qubit influences immediately the state of the second qubit, and this is called entanglement, right? Entanglement is one of the power of quantum computing, right? And it's a global phenomenon. If I have here, I depicted a status of 4 qubits of a quantum computer. If I manipulate the left qubit, right, I fiddle around with it, the others are unaffected. But if I create an entangled state, and I will show you how easily this can be done, if I manipulate now the left qubit, all the other qubits are dancing too, right? That means it's a global phenomenon. Fiddling around with one qubit immediately manipulates the other qubits of the same state too. And this is unique for quantum computing. You can't emulate this physical effect in the classical world. And you can prove that every computation that is not involving entangled qubits can be performed with the same efficiency with classical computation. But this is something that I need to explain is only with a grain of salt, because while you can simulate quantum computing, of course, it's linear algebra at the end, and you can use supercomputers to build huge high-dimensional vector spaces and manipulate them. But keep in mind that 2 to the power of 50 already corresponds to petabytes. You need a huge cluster to simulate 50 qubits, and in fact, only very few computers can simulate quantum algorithm up to 50 qubits. But think about that you have 80 qubits. 80 qubits, if you if you perform the calculation, would require every atom on Earth to be a storage cell to store the state of the quantum computer. That means beyond 50, you can maybe simulate 52, 53, 55, but if you reach 80, you would need the whole planet and each atom would be a storage cell to store a single state in the quantum computer. So simulation is only something that can theoretically happen, right? But you can prove that in theory, if you have infinite amounts of classical storage, if you don't use entanglement, don't exploit entanglement, then you could simulate the quantum algorithm. But you can prove that every quantum algorithm that shows an exponential speed up compared to classical algorithms must exploit entanglement, right? And we will see that there are a bunch of algorithms that are exponentially faster than the best known classical algorithms. And this is what I show next. I have here a couple of examples here. For example, you can compute prime factors of a number that is only polylogarithmical, while the best known classical algorithm is exponential. You can speed up unstructured search with polynomially. You can have molecule simulation exponentially faster. You can solve linear equations exponentially faster. You can compute eigenvalues exponentially faster, right? So it has a lot of bunch of speed up, and many more speed ups have basically been shown by quantum algorithms. I don't want to discuss the details. This is the Shor algorithm. It has a lot of stuff here that is done on the classical computer, like computing the greatest common divisor. And here what you see here is we need to compute the period. If I know the period of this modular exponential function, then I can compute a prime number with polylogarithmic time. So the overall runtime of the Shor algorithm is in the order of logarithm n, where n is the number that I want to factorize to the power of 4, while the best known algorithm, you know, that is 2 to the power of square root of m, where m is the number of bits that I need in order to store the number m. And you can show that the larger the number is, so k, so to speak, is the number of prime factors, the larger the number n is, and in RSA it's a huge number, the more likely is it to find the prime factor in very, very, very few steps, right? So this can be cracked. So it's an exponential speed up, and this was a shock in the 80s to most people that you can factorize numbers. Here's a little comparison. Here's the exponential growth of the best known classical algorithm. Here's the Shor algorithm, and the next slide is even more shocking. Under the assumption that you have an error-corrected quantum computer, which we don't have today, optimists say we have it in 5 years, pessimists say in 20 years. So if you take 10 years as a middle, that's absolutely fine, right? You know that RSA has the RSA 2048 has been created in order to prove that you need the age of the universe to crack a key. This is called the RSA challenge problem. If you use a quantum computer with different processing speed here, by the way, today's quantum computers already have 5 gigahertz, right? Then you crack that thing within a minute. But again, it requires an error-corrected QPUs. Today's quantum computer can only crack small numbers, right? So this is a real threat that we as a society have, right? Remind that many people need to store documents confidential for many decades. And if you store documents today and think they are secure, no, they are not secure, because in a couple of years we will have error-corrected quantum computers. Then we can decrypt each and every secret that we have stored anywhere. And think about the impact on our society. No online banking, no online shopping, blah, blah, blah. Everything will be basically gone. But how do you program these beasts? Right? Well, here you manipulate, as I indicated before, a single qubit by unitary maps. H2 is the two-dimensional complex space here, right? It's a 1-qubit operator, and there are 4 qubit operators that are of utmost importance. These are the Pauli matrices. Pauli is a Nobel Prize laureate in physics. This is a negation operation, forget what the others are basically doing. So the X, Y, Z are the Pauli operators, and there's another important matrix, the Hadamard matrix. These matrices are the workhorses in manipulating single qubits. And the other workhorse is a 2-qubit operator. It's a controlled knot. This is the graphical representation. A controlled knot means if the first qubit X is in state 1, then you negate the state of qubit Y. And if X is in state 0, then Y is unaffected. It's a controlled knot. The X is the control bit and Y is the target bit. And you can prove that based on the Pauli operators and the control knot, every quantum algorithm can be written. Right? This is a universal set of gates that the quantum computer manufacturer needs to implement in its hardware in order to support each and every quantum algorithm. We have graphical tools. What I show here is Ibm Quantum Experience. You see here the gates that you can use. Here the horizontal lines are the individual qubits, right? You can of course add as many qubits as you like, and then you drag the 1-qubit operator to the canvas, as I did here. Right, the plus is the Pauli X, because plus means you have addition modulo 2. At the left side, every qubit is in state 0. So Q0 is in state 0. If I negate it, it will be in state 1. If I measure it, this crazy thing here means measurement, then I store it in the classical register number 0, right? And so what I observed then on the simulator is in fact that in 100% of all my measurements, I get a 1. But if I perform the same on a QPU, I only get 94% ones and 6% zeros, right? And this is because of noise, right? The quantum computer is affected by the outside world, right? Rays from the outer universe will hit the qubit. This is why it's then basically destroyed. We will call it decoherence. And what we see here on the right side is that what I create here graphically is assembler code. This is a standard open QASM. Many vendors do support it. And so it's really assembler. What you see here is I initiate a quantum register with 2 qubits, a classical register with 4 qubits. The qubit 0 will be negated by Pauli X. Then I measure the qubit 0 and store it in the classical register C0. So it's assembler. Here, if I use the Hadamard gate on the first qubit that is in state 0, remember the default is the machine is in its ground state, it's 0. Then if you perform the little math here, then you create superposition. Right, out of 0, if I apply Hadamard on the first qubit, then I get the status in superposition, 50% zeros, 50% 1. And here is the quantum assembler. And if I measure it, then again, I get this distribution here. So a quantum algorithm is always performed multiple times. Each execution is called a shot. So typically you have 1,000, up to 10,000, 20,000 shots, and then you get this distribution. And what you have, and what you can prove is that the most probable result will be the result. Right? You can perform something that's called the Chernoff boundary that you may know from probability theory. Right? The most probable result will always be emphasized. The often you perform a quantum algorithm, the more will the correct result be amplified. Entanglement is created quite simple. You bring the first qubit with Hadamard superposition, then you apply the C0 between the first and the second qubit. And what you see here is, here's the calculation, right? You create this state that I have shown you before in order to motivate entanglement. This is an entangled state that is the real power behind quantum computing. And if you measure it, roughly 50% really, you have the state 1,1 and the state 0,0. So as I indicated before, even if I have the ground state and I measure it, right, you don't get the ideal values only in a simulator because of noise. So this basically means means the following: a qubit may randomly decay from its original state, here the red state, into the diametral state, the green state. This is the relaxation time, right? The collapse from its state to the diametral state. And dephasing means the qubit is a little bit shittering, right? So it changes a little bit the angle on the Bloch sphere, which is called dephasing time. So qubits are not stable, but over the time they decay, right? Today we have a couple of milliseconds that a qubit basically is stable. Similar is true for the individual operators, right? What you can do is you can represent each operator of on a qubit as a collection, as a series of rotations. The Bloch sphere in a three-dimensional space, x, y, z are the x, y, z axis, right, of three-dimensional space. So each unitary operation can be represented as a rotation around the z-axis by an angle delta, then around the y-axis, then again around the z-axis, right? So this is how you can represent each and every unitary operation. And this is, by the way, what is done by a quantum compiler. As this quantum assembler is basically transformed by a compiler into a set of rotations. So each circuit at the end is a bunch of rotations and C-knots. What does that mean? Well, a rotation around irrational numbers is never correct. Ignore multiples of pi or fractions of pi, right? You can rotate around 90 degrees, but not around 90.1100 blah, 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 and so on, right? So each rotation is inherently imprecise because you can't rotate exactly around the angle theta that you want to rotate your qubit around. That means each unitary operation as a series of rotation operations has a very small error, but it has an error. That basically you need to control the number of operations, because at the end errors are piling up. You can prove that they are piling up linearly, so it's under good control. That means you want to limit the depth of your algorithm. The depth basically means if you draw the algorithm as I've shown before, like in IBM Quantum Experience, right? Here you have the different gates. This is a 1 qubit gate, a 1 qubit gate, a 2 qubit gate. Gates can be executed in parallel if there are no data dependencies, right? This gate, G11 and G21, have a data dependency because G11 manipulates this qubit that is input to gate G21. So they need to be executed. So G21 needs to be executed after G11. That means you can arrange the gates into these layers here. And the number of layers that you need, the minimum number of layers, is called the depth of the algorithm, while the number of qubits that are manipulated, note that this qubit is not manipulated, this qubit is not manipulated, is called the width of your algorithm. Here's an example. This is what I've drawn in my graphical editor, and you can see that the S can be shifted over here, the H can be shifted over here, the T can be shifted over here. So what results is this circuit, and instead of 1, 2, 3, 4, 5, 6 layers that I, as an innocent algorithm designer, have drawn, right, the compiler will basically detect that this is of level 3, and so depth is 3 and the width is 3 because only 1, 2, 3 qubits are manipulated. So these algorithms are noisy because the qubits decay, the gates show a certain error. That means you must control the size of the quantum algorithm, where the size is measured by the width and the depth. And the very rudimentary rule of thumb is that the width times the depth must be really smaller than 1 divided by epsilon, where epsilon is the error rate of the quantum machine. The implication is, well, you can decide whether you need many different layers to execute your algorithm. It's a deep algorithm, but if D is large, W must be small in order to fulfill the criterion. W times D is significantly less than 1 divided by epsilon. That means you have only very few qubits that you can manipulate, but very few qubits can be efficiently simulated. So 30 qubits, 20 qubits can be simulated on your laptop. 30 can be simulated on a server, right? 40 can be simulated on a cluster. So in order to show quantum advantage, you need shallow quantum algorithms. You need to manipulate many qubits because this can't be simulated classically, but then you only have a certain depth, right? Only very few layers can be executed one after the other before a noise hits you, and then your results become too imprecise. So, and that means these shallow algorithms is what we study today in the so-called NISQ area. NISQ is noisy intermediate scale quantum. And you may be reminded to KISS, complete instruction set computing, RISC, reduced instruction set computing. So this is a play with words, right? NISQ means noisy intermediate scale quantum. So noise means you need to leave the QPU as soon as possible. That means the algorithm that you need to that you run on your quantum computer must be short. Then you measure the result, what the algorithm has produced, and then you go to the QPU and you analyze your algorithm. And we call this a variational algorithm because the algorithm that you run on the quantum computer depends on certain parameters, right? This parameterized circuit produces a result. You have a certain cost function that is problem dependent. The problem that you want to solve, computing eigenvalues needs another cost function, then optimizing certain clauses. So you optimize your cost function and come up with new parameters. Then you go again to the QPU, and this is why we call it a variational algorithm, because you loop between the QPU and the CPU in order to use the power of the QPU within the decoherence time. That means the goal of a variational quantum algorithm is that the execution time TU of the algorithm proper U is within the decoherence time TD. And you will be surprised, measuring takes longer than computation. That means that the measurement time also must be still within the decoherence time. That means the execution time of the circuit, TU, must be small enough so that TM is still less than decoherence time minus execution time. And this is the overall goal of this variational quantum algorithm. And if you invent an algorithm that satisfies this simple inequation, then you have an algorithm that is suitable for today's quantum computers. And we have many different kind of variational quantum algorithms that can be implemented today. Here I show you two. One is the variational quantum eigensolver that is used to compute eigenvalues, and you know that eigenvalues are very important in many different applications. And you can optimize and you can compute combinatorial optimization problems by a class of algorithms that are pronounced QAWA, Quantum Approximate Optimization Algorithm, QAWA. So that basically means, what is the structure of today's algorithm? So variational algorithms, and here you see these algorithms are hybrid. Hybrid in the sense you have a quantum part and you have a classical part that here in this case does some optimization. And this structure is trivial. So if you draw a workflow out of it, and I use here a little bit of BPMN, right? Then you execute your algorithm, which is called by physicists an ansatz, right? You execute on a quantum computer. This icon means quantum computer. Then you have a classical computer. The hammer means the classical piece of code. So you evaluate the cost. And if some convergence criterion or termination criterion is met, right, then you have the result. Otherwise, you optimize your parameters, feed them back into the quantum computer, into your ansatz, and so on. So you loop around. So it's a very simple structure. It's a process here. But here I have something. So we are using a lot of quantum machine learning and work with industry partner on this. But here is a real world scenario, and real world means only a subset of the real workflow that we need to run. So you retrieve some data, and in our use cases, this data is categorical. That means it's text-based data, but most machine learning data analytics algorithms are assuming that your data is numerical. So what you need to do is you need to transform your textual data into numbers, We do this by computing some sort of distance matrices. We use MDS, multidimensional scaling, in order to embed then the resulting distance space into a vector space. Right? Then you compute a covariance matrix because we want to perform principal component analysis. So we compute the covariance matrix out of this. Then we use this algorithm that I mentioned before, variational quantum eigensolver, to compute the eigenvalues of this covariance matrix. Then we perform PCA, principal component analysis. Once we know our features, we compute a certain graph, because here we use max-cut-based clustering algorithms, right, blah, blah, blah. And then at the end, we use Quawa in order max-cut can be reduced to a combinatorial optimization problem. So we use Quawa in order to compute here the clusters. And then we go on, right, we label data automatically. So you have a real workflow. Means here the quantum computer is used only in places where the quantum computer shines. So in fact, what you need in a quantum application is a lot of classical code. And so what we, what we do here is classical code is involved. And here, for example, I show you what retrieve data means. Right? We all know this, right? Retrieve data, in our case, is a Java program that runs in the JVM that is hosted on a server machine. In order to retrieve the data, I connect to a certain database that is managed by DB2, that runs in requires an operating system that runs on a virtual machine. And we all know, we are aware of cloud computing. This is called a topology. So the pieces of artifacts that you need and their dependencies, you need to deploy this. So you describe it as a topology, and all the artifacts that you need in order to retrieve the data can be packed into what we call a quantum application archive. In our case, we use here a standard called Tosca, topology and orchestration specification for cloud application. It's a standard that's supported in industry. What you can also do is, out of this Tosca representation, you can transform it into Kubernetes and so on, or into Ansible, you name it. So you package all the artifacts of your application together in order to have the application as an artifact, so that others can use and deploy it in your environment, on premise, in your company, or in your lab. You deploy it based on provisioning technology, and then you can run it. So in fact, you know, workflows are called, in modern terms, orchestrations. Deployment is called orchestrations. So what you have here, I play with words, you need two orchestrations in superposition. The workflow is executed in order to run your quantum-based application. And whenever the workflow detects that a certain piece of code needs to be invoked, then the provisioning engine comes into the game. If you do provisioning on demand and the corresponding topology is provisioned, then the code is run, and after that it will be deprovisioned to save costs. But we go even further. So here is a snippet of the workflow that I've shown before. And of course, the classical code can be realized based on modern technology, based on an API. So all the algorithms that we provide, open source, are rendered by API. They are offered by means of an API, and the implementation, of course, is done by microservices. Typically you have multiple microservices that use each other in order to implement the API. It may even be that one microservice calls another microservices outside of the domain of the API. Then, of course, you need, that a data plane, that means you need proxies like Linkerd or Envoy. And then you have here the overall data plane. So the microservice thinks it talks directly with the other microservice, but this is done based on proxies. And proxies can be dynamically installed and deinstalled. The same is true for microservices, so you need to discover them. This basically means you need a control plane. Typically, this is Istio in Kubernetes in environments. So this is all the stuff that comes together, right? If it comes to classical code, that you need classical code in your quantum application. You need all the machinery that we developed in cloud computing, right? APIs, microservices, data planes, control planes, provisioning, and that like. So the required middleware includes but not exclusively. We need more a workflow engine and a provisioning engine. The workflows must be modeled. The topologies of code that must be provisioned must be modeled. You need an API manager to throttle access to the APIs, to authenticate people, to manage payment. You need a service mesh because everything is dynamically built for scale and so on. This is what we basically need in this environment. So this is here the overall environment, right? The service mesh controls the cloud. You have the QPUs here in the cloud, Quantum as a service. You need the API manager, provisioning engine, workflow, and storage, where the archives, the applications, Quantum application archives is stored, the Quantum programs that are invoked, and that like. So what that at runtime, this is a little zoom into the runtime. In quantum computing environments, right, you send a message to a queue that is front-ending a quantum environment. There is a queue controller. The queue controller basically interprets the message, and if the message indicates that this is not only a single algorithm on a QPU, but a workflow, the workflow engine is basically informed. The workflow engine will fetch the workflow that is somehow encoded in this message here, fetches the workflow, instantiates and executes it, goes against classical code that runs in the cloud here, goes against the QPU if it needs to execute steps on a quantum computer. This is theory, and then of course you can monetize it, right? So you need these quantum application archives can be stored in a marketplace. By the way, I show you that we have implemented this in some project. There's a marketplace where all this hybrid quantum applications are basically stored. And if you pay for it, you can buy one out of the marketplace, or you can run it on demand and only pay per use or per time. And this application, as I said before, the workflow not necessarily includes the classical code itself, but it may go against APIs. So what you need is an API manager, because the workflow uses some classical code, some optimizers, for example, that other people have implemented for you and have offered as an API that is registered in an API manager. That means you can invoke it on a per call base, or you pay for 10,000 invocations. Throttling, for example, is managed, scale is managed, security is managed, and so on. And this is how you can make money out of it, right? You can sell applications, or you can share it open source, of course, just for free. And you have APIs that you can sell or offer just for free in the cloud over the internet. So we have prototyped it together with IBM. We used the IBM environment, we use IBM Cloud, and IBM had to change a little bit in the quantum computer to make that all happen. We use a BPMN engine, in our case Camunda, and we use the provisioning engine OpenTosca. This two orchestration that are working intertwined, as I've shown before, right? So when a request comes in, right, the workflow is kicked off in the Camunda engine, right? Topology is basically the applications are installed on demand, provisioned on demand. We interact with the Qiskit runtime that we invoke circuits and so on. But because workflows are old-fashioned, some young people say workflows are old-fashioned, so we wanted to do something more modern. What we then did is we did a second prototype together with a company called WSO2. They have a low-code environment. Low-code, so to speak, is some people call it citizen programming. That means each and everybody can implement low-code programs. The low-code environment is Choreo, and we basically use Choreo to model our workflows. So the quantum applications are then low-code applications, and out of the low-code environment, we invoke, as before, circuits on an IBM quantum computer, and also on other quantum computers. Right. So two different prototypes. One is workflow, and one is based on low code, just to prove that all the concepts are independent of the underlying classical technology. So how do you build these beasts? So what I said before is you need classical code. So software engineering has a bunch of life cycles how to build classical code. We have workflow life cycle that must be adapted in order to build quantum workflows. Then completely new, how do you build quantum algorithms, quantum circuits? How do you manage all that stuff? You need an operation life cycle, right? DevOps, right? Like that one. And to the outside, right? You export important steps that you need in the various four life cycles here to the outside, so that you give the impression that this is the quantum software life cycle. Let me dive in the next remaining 10 minutes into some of the steps that are performed here. So this is our proposal, how such applications are built. We are running a project funded by the German government that has about 40 million funding with tons of industry partners, and they basically realize we need a software engineering discipline in order to build applications, and here's our first attempt to do that. Right, so how do you architect and design your overall application? Well, what we are doing is we are building currently a quantum pattern language, right? A pattern, if you recall that, is a proven solution to a recurring problem. It's not code, but it's a document called a nugget of advice, right? You document how to solve a problem, right? And one pattern typically refers to another. A pattern says, if you have the problem that I'm solving, you very likely have the other problem. So look there, how to solve the other problem. It's a web, it's a network of patterns that people call a pattern language. Right, so here's a little excerpt of the pattern language that we basically built so that our industry partners can basically take a look at this pattern to find out how to build quantum circuits. Right, we built something that is called the Pattern Atlas. The Pattern Atlas is a tool, right? It's available under quantumcomputingpatterns.org, where you can basically see the patterns. And if you click on one here, you see this kind of document that sketches how to solve a certain problem. Here I solve a problem to create a very high degree of entanglement of your quantum register. Often you need to control the degree of entanglement, right? Some states can be only a little bit entangled, and some can be very tightly entangled, and the Schmidt decomposition controls this. Another example is how to decide whether you perform something on a quantum computer or on a classical computer. So this is the big question that everybody has that works with quantum computing. When to use quantum, when to use classical. For this purpose, we built a tool called QANA. It is called Quantum Humanities Analysis Tool, because we wanted to make the tool as simple as possible. We wanted to test it with people that have no affiliation with computer science. This is why we work with humanists across a bunch of German universities, and they test the tool, and because they have no clue is wrong. They are not affine to quantum computing. If they are satisfied, then others will be satisfied too. So QANA is an environment that implements for the same problem a bunch of classical algorithms and a bunch of quantum algorithms, and you can basically perform experiments. You can pump your data into the environment, then you run classical algorithms and quantum algorithms and see what the outcome is. We even allow you, of course, to fiddle around with the hyperparameters of the algorithms just to show you, just to let you experience which settings will satisfy your need. Here, for example, I show the classification part right here. If you click on that one, the context menu comes up, and then you see the hyperparameter of here, for example, it's the hyperparameter of this quantum support vector machine, right? It's a quantum support vector machine. Right, here we have a bunch of clustering algorithms, right? Here, these are quantum implementations, classical implementation, quantum implementation, and so on. So a bunch of implementations that you can basically fiddle around with. This is, of course, also available open source on GitHub. Next thing would be how you model your stuff. This is very simple, right? We use Camunda Modeler in order to build this kind of workflows, and for this purpose we extended Camunda Modeler because we needed a couple of new task types that are quantum specific. So this is also available open source. You can use the extended Camunda BPMN modeler in order to build workflows that indicate that you need some specific quantum specific steps here. Well, how do you analyze and then analysis and rewrite? So what we have shown before is this variational quantum algorithm is a loop in a certain workflow. But what about if you have a huge workflow? So what we are doing is, if somebody models a huge workflow, we analyze the workflow and detect fragments, sub-workflows that may benefit to be bundled together to avoid latency because the queue-based access. What I told you before is a message is stuck into a queue in front of the quantum computer, and then you wait until the quantum computer dispatches your queue and execute your message and executes the quantum algorithm. There's a certain latency involved, and in order to reduce this latency, IBM has announced a new runtime that allows you to allocate the quantum computer for you for a certain time slice so that you don't suffer from this latency. Furthermore, in order to move the data, if you pre-process this classically, but then at the same time you need to move the data out of the cloud close to the quantum computer, this new runtime concept allows you to deploy the code that produces data that your algorithm needs very close to the quantum computer. So what we do is we detect fragments in the workflow that can be packaged together and dumped very close to the quantum computer. Right, here is what we are basically doing. You send us this workflow, we detect candidates for the new runtime, then we filter the candidate, this one remains, then all the code that is needed here, so we build a new package, right, a Tosca file, so to speak, and contract this sub workflow into a single step that is then executed in the hybrid runtime. And of course here, this stuff that we compiled here is deployed into this hybrid runtime. So we do some optimization. This is something very initial what we are doing. There can be done much more in order to optimize these hybrid quantum classical programs. Another thing would be, quantum hardware selection. So there are a bunch of hardwares out there. Some are open that you can use without paying for them, but because in our project we partner with a couple of quantum computer vendors, so we pay them, we execute them, but then you have the problem, which QPU is suitable to execute my circuit. Right? Remember that one simple criterion is width times depth is significantly smaller than the error rate, but we do much more. So the circuit basically is translated based on the different SDKs that the different quantum computers do support, right? Then we compile them based on compilers that come with the quantum computers. Then we basically access a database that we are maintaining, provenance information about the current decoherence time, the current gate errors, many different values that we basically have available that we use in order to evaluate the compiled circuits. Each user then we rank the circuits, we rank the QPUs that are available and provide the highest success rate at the top in order to run successfully your algorithm. Then we basically execute it, and then we maintain the results and basically use machine learning to adapt our ranking algorithm here. So this is here a little snippet about this NISQ analyzer. Right here you see a bunch of criteria that we do consider in order to compute this ranking here, the number of the depth that I've shown before, the number of measurement operations that is important, right? What are the single qubit error, the multi-qubit error, and so on, and many more criteria are basically here considered in order to provide this ranked list. And then you can execute the ranked list. You double click here, and then we submit it to this quantum computer, execute it here, maintain the history of the execution, to use machine learning to basically adapt these weights. What you see here that I did not mention are the weights of the criteria that are important to decide to compute this ranked list. So we adapt this. Another thing is, how do you optimize your quantum circuit? Well, often I skip to that. Often you can split it. If you use many qubits, sometimes you can split your circuit into a set of circuits then you submit the fragments of the circuits to different QPUs. They spit out their results, and then you can combine the results. You can't do that always. For example, if this part of the quantum computer is tightly entangled with this part, you can't split it. So we are analyzing the circuits in order to find out the degree of entanglement, and then we find a proper splits here. That cannot be done always, but often. Another thing is now in the operations life cycle. If you have tested everything, right, you computed, you developed your classical code, your quantum circuits, your workflow, then you need to run it. So first of all, you need to define the topology of your application. And as I've shown you before, we use the so-called winery. Winery is an open source modeling front end for this standard Tosca. And then you build your quantum application archive. And all of this is then bundled into an environment that is already available as open beta under community.planck.com. Planck is the name of the project that is funded by the German Federal Ministry of Economics. So the platform has an open source, an open part that you can already access now, right? It allows you to take a look at the quantum algorithms, at the patterns, at the applications that have been built that implement the algorithms. You have data available soon, not yet. The public beta does not yet contain this data because we are focusing here on quantum machine learning. We have this provenance engine that accesses the different quantum computers in order to get aware what their current state is, decoherence time, gate fidelity, and so on. This NISQ analyzer is available in order to analyze your quantum circuits. You can handcraft your workflows that will then execute based on this access layer on these different quantum computer machines. And if you don't find a solution in this open platform, we have a marketplace here, and this marketplace basically allows you to say, okay, I don't find a solution for my problem in the open part. Then you can store a request for help, and then you have providers, like consultant companies or developers may take a look at this requirement database, and then you make a deal between the customer and the provider to build an application. And here the marketplace also contains here this packaging and provisioning engine that then submits the newly created application to a cloud and quantum environment, as I've shown before. This is here the GUI of this community it's platform.planck.de, right? This is the first GUI, and if you double click here, right, then you get much more. So this is a consortium. As I said before, it's about 40 million funding of the overall project. Right, these are the consortium partners, and we have nearly 80 associated partners. Here is only a subset of it. We have 4 research partners, and the rest are industry partners that are testing what the research partners are basically building. They run their use cases. We have more than 30 non-trivial use cases, real applications that help the partners and the associated partners to solve their problems on the quantum computer. So the conclusion, to leave a bit of time for questions, if there are questions, is what I try to show is that many quantum algorithms are already out there that provide a speed up compared to the best known classical algorithms, often an exponential speed up. Quantum algorithms are very different from classical algorithms, but you need very different skills to solve a problem with a quantum computer. So what we see is you need mathematicians or physicists as of today in a project that solves a problem with the quantum computer. So that brings new kind of problems in the software engineering life cycle because new roles are appearing here. That I also showed that most quantum applications are hybrid, will be hybrid even in future. That means you need to combine quantum parts as well as classical parts. How to build such applications is completely open, right? The research in quantum software engineering just begins, right? We have a conference at IEEE Services Quantum Software, QSW, in this July in Barcelona. First big conference. We had a couple of workshops before, and the cloud is a proper execution environment. So you have quantum computing as a service. You need provisioning technique, orchestration technique, service meshes, microservices, and all that like. And we begin to understand how to plug everything together in order to make this quantum application run. Thank you very much for your for listening to the talk, and I hope we have time for questions.
Thank you, Frank. Really great talk.
Thank you.
So really, I want to remark you, it is really impressive, the work you are presenting us. It's really challenging. Repeat, I thank you for this presentation, because you know, keynotes are people that inspire the researcher, and you know, you inspire very well, and let me say thank you. There is any question from the audience? So I have a few. Go ahead, Alessio. Can you bring the mic to Alessio?
Good morning. Thank you for the presentation. And so this presentation says us that quantum hardware is quite available for everyone thanks to cloud approach. So should we be scared about our security system? So we have C-short algorithm, for example, and we see that RSA could be broken in an easy way. Should be scared about that? And so I have another question related. Does exist other example of algorithm that solve problem used in security, like for example discrete logarithm on elliptic curve for quantum computing? Thank you.
Yes.
Thank you, Alessio.
Should be scared. We should be scared like hell, right? It is so while government is funding a lot of quantum computing projects, only very few projects are funded in quantum security. So as I said before, it will take at least 5, very likely at least 10 years to crack these RSA keys, but they will be cracked. And as I tried to indicate it, the security problem is out there already now, right? Because many companies need to store information confidentially for a long time, and if these they are decrypted based on current algorithms. But what you can do is you can prove you can build a new infrastructure that is based on symmetric keys. There are algorithms, quantum algorithms, that exchange securely symmetric keys. You can basically detect wiretapping symmetric keys. This will be then secure. And for example, in China, they are building already a quantum communication infrastructure that requires so-called quantum channels. They use laser light that, so you build a communication instruction from city A via a laser beam to a satellite, the satellite back to city B, and then they communicate securely about that. So they are preparing. The European Union began a few projects in this domain. So we know that if the quantum computers are powerful enough, our today's security infrastructure will be gone. Although there's work on post-quantum security. Post-quantum security means we are investing in algorithms that cannot be cracked based on our today's knowledge by today's available classical or quantum algorithm. So the NIST took a look at, I think it were 25 algorithms, and 10 algorithms did remain. They are standardizing these algorithms, and people begin to build something that is called an agile security infrastructure. Agile means if you want to encrypt something, you use randomly one of the quantum safe algorithms, and if one of the algorithms in future will be cracked, because as I said before, these post-quantum algorithms cannot be are safe today, but we cannot be sure that they can be cracked tomorrow by classical or quantum algorithm. So if one of these post-quantum algorithms is cracked, you plug it out, and the others do remain. Right, so this is what currently, so, and of course, source algorithm can be extended to have discrete logarithm, as you pointed out yourself. So we should be scared, and you see that I'm nervous, so I'm running every month to the German government and say invest more, although I'm not a security specialist, so we do need that.
Great, Frank, thank you. Really good idea. There is any other question in the audience? Please, Sarah, thank you.
Thank you. Hi, Pascal So, Loughborough University, UK. Thank you for the talk. Really, really interesting. My question is about the hybrid approach, where I'm confused, probably because I'm not in this area. And then, is it a transition, more like transitional period that you need this hybrid approach, and then in the end we will move on to like fully quantum?
Very clear answer: no, it's not a transition period, because, for example, the Shor algorithm that you saw is a hybrid by itself, right? It only uses a single little step called the quantum Fourier transformation in order to determine the period of this module exponential function, and the rest is classical computing. You can compute, for example, you need to compute continued fractions, whatever that means, right? So what most people say is we will always have both classical computers like quantum computers, like we have GPUs in classical computers, FPGAs and classical computers for the next many years. Quantum computers won't take over. Although in theory you can show that the quantum computer can perform each classical algorithm, most people say it's much too cumbersome to re-implement everything on a quantum computer. So my best guess is, for my lifetime, and maybe your lifetime too, quantum computer will be special processors.
Thank you.
Very well, thank you. There is some other question. So I have a question, Frank. I remember when I attended, there was a conference in Washington with IBM people before COVID. They mentioned the challenge in creating compilers. I understood that now we have some much more mature field there because you have to adapt the algorithm on the circuits, on computing, on quantum computing. Do we make some progress on that? There is some room. What is your opinion on compilers, editors and compilers?
Okay, so of course, each and every vendor has its own quantum compiler, right? Be it Rigetti or IonQ or IBM, they have their own compiler, but there are cross compilers, right? For example, a company that was formerly called Cambridge Quantum Computing, now called Quantinuum, they have a compiler called Ticket, right? We experimented with it. They compile better than most of the provider-specific compilers. There's a group in Toronto that is building one. I don't have experience with this compiler, but I hear people saying that it is as good as this Ticket compiler. So we made a lot of progress in this kind of vendor-neutral compilers, Massimo.
Very well, Frank, very well. So let's say thank you again to Frank for a really brilliant talk. Thank you, Frank.
Thank you. Have a good time and enjoy the conference. And I'm sorry for not being there. I love to be in Italy. I know that Massimo is a very friendly host, so enjoy the conference.
Thank you, Frank. See you soon. Bye. So I have an announcement for all of you. Keep in mind, no social dinner for you all, okay? If you don't have the ticket. You need to take the ticket, okay? It's in the registration area. You can ask the people there, okay? Because you are on the list, you make the registration. There is also some people with some extra tickets for guests, okay? Keep in mind, the social dinner is 8 o'clock in the floor upstairs, okay? And that's it. You can move in the rooms, okay? Thank you, everybody. Bring with you the badge or some ID to be recognized, of course.
like. Okay, then we'll get started here. Thanks for coming to the session on distributed middleware and network architectures. We'll get started almost on time here with the first talk by Heiko Ludwig, decentralized allocation of geo-distributed edge resources using smart contracts.
That's the microphone. Okay, great. And how does this work? Up is forward. Yeah, thanks. Good morning, everybody. It will be difficult to follow up on the kind of keynote, but I'll try my best. This is joint work with the primary contributor really being Jinlei Shu, who can't be here today, and Balaji Palanisamy. I always have to be careful getting the name right. As his advisor, there's another student also working on it, who's now a professor at Louisiana State, and I'm Heiko Ludwig. In my day job, I lead the distributed AI research strategy at IBM, and that's kind of a part of this work on resource allocation. So the whole point here is how to work with geo-distributed resources and how to allocate resources in that scope. Right. Or not? Sure, maybe it's the other way. Oh, it's the other way. All right. So I'm still figuring out this device. So it comes to no surprise to you that the Internet of Things and distributed computing at the edge is booming. Everybody of us has a lot of devices in our house that generate a lot of data and consume a lot of data. And I think everybody has a device they can talk to in their environment, and so do I. And that generates a lot of data. So that's a big booming space, and we find a lot of IoT applications that really help making sense to this. We have smart city environments, smart home environments. We use a lot of wearables. I guess a lot of us have these smartwatches going on. We have connected vehicles today. Our vehicles give support and navigation and location and a lot of other things. Applications are more sophisticated. Industrial is also an important sector. In industrial applications on the shop floor gets more and more smart, and healthcare, of course. A lot of these applications have quite stringent latency requirements, right? So response time is very important, in particular then down in telesurgery. You really want to make sure that your equipment works well there. Here's kind of an interesting graphics, the one at the very bottom right, where you see a kind of a split up between the required throughput of an application and the delay it accepts, and then the space of virtual reality and so forth is not unsurprisingly the one that really benefits a lot from or requires low latency and high throughput. Oops. Wrong direction here. My apologies. So one of the key problems here is let me just step through this. Is the latency requirement. So in the streaming applications we already have today, you usually solve latency requirements by content delivery networks, right? You move the content closer to where the consumer is, and then your Netflix video just streams like a champ because it actually doesn't come from some Netflix server way in the background, but it comes from content delivery networks that are much closer to your point of consumption. Then you have that, then the back end of the network. However, for compute, it's kind of just emerging, right? And sorry, and just get on with it here. Sorry, and that's where edge computing comes into play. So in edge computing, that's kind of the idea of moving mini data centers, small data centers, away from just back in the cloud, but putting it closer to the point of consumption. And there could be many different things, right? There could be, on the one hand, just a telco provider providing a data center closer to the point of consumption in your neighborhood, in your region, in your city. It could be let's say on an oil rig, you might have a mini data center. You have it maybe on a cruise ship, right? Something mobile. So there are many different variants of this, maybe even in something like a car, a very sophisticated vehicle, or plane. You might have a mini data center that moves around. And so that brings kind of the compute closer to where you really are. And then what affords it to you is low latency, right? So you don't need to communicate back and forth so far. You move the compute closer to the point of consumption by your end user device. One of the problems that we have today is that oftentimes the mini data centers that are close to you are coupled to your service, right? So that a particular company who provides a service would set up a local data center close to you, and oftentimes you find this in industrial applications, for example, where it makes a lot of sense, where you would have a company, for example, building small data centers in manufacturing locations to avoid latency in their robotics, for example. But obviously that's just for a single user. Everything there is done on behalf of this particular company that manufactures cars or whatnot, right? And the problem obviously is that if everybody has if you roll this out, this scheme in a broad sense, if everybody builds their own, every service provider builds their own mini data centers, they might not be optimally used, and so you have to make some compromises in terms of latency. So you can only build that many. On the other hand, we have this model of content delivery networks where we have content delivery companies like Akamai just putting these services everywhere, and you could imagine a similar scenario here in the compute space, where people basically put mini data centers out there and rent the space, if you like, and so in a way a cloud service provider would do. And we see this a lot in the 5G networking environment. I think that's part of the model there, that you have that. So what could you do? On the one hand, we have this fixed allocation. You could imagine that you would have, let's say, a cloud service provider, Amazon, Google, whatnot, kind of build a lot of these small micro data centers out there, or telco providers who already have infrastructure in many different places, and you buy it from them at fixed price, right? So in the way that cloud computing mostly is fixed price. There's some variable pricing. Sometimes you get discount. But on the other hand, you could also look at variable pricing, where you have basically auction off or sell off resources for particular applications. Let's say you would have, let's say, a video game that's very interactive, some shooter game that's very immersive, or you have a something like that is very latency sensitive, and depending, a new game comes out, right, and a lot of people start playing and then want to interact with each other and into the exchange state, and it's really important to get the compute closer to these gamers and players, right? So in this case, it would be nice if you could kind of dynamically acquire resources where your new clientele is, and for that matter, then you would have some kind of a dynamic allocation service, basically auction off your capacity. And in this case, you could do the centralized approach, where you have a service provider that's kind of the company that, for example, runs a game, buy capacity from an edge infrastructure provider, and then you have an auction service by a centralized auction coordinator who sells off that, hosts the auction, and then you would buy pieces of capacity. And nowadays we'd use a container of a particular capacity for an hour, for example, that you could use and buy that. Centralized solutions do have a few problems, though. Here's some terminology we find here on the right side. So you have these two service provider, infrastructure provider, and the coordinator. And then the idea is that you generate a resource contract. It's basically a kind of a guarantee that you can use a certain compute capacity with a container for 1 hour, let's say. There's some ups and downs of using a centralized coordinator, right? There's some problems of having a single point of failure. You have to trust that auction facility a lot. If depends on how it's implemented. So there's you can think about how to require. There are all these problems of trust and single point of failure and so forth can be solved in different ways. One way of trying to do that is decentralizing it, and basically that's what we try here, replacing basically the function, the main auction function, with a smart contract. And a smart contract, I think many of you have heard the term, but if you haven't, it doesn't have a lot to do with a contract. It's actually a script, right? A script whose execution can be monitored on a blockchain. So, and that's kind of what we try to set out to do that, and that's what the main premise of that. So in our approach here is based basically on Ethereum blockchain, and with the usual accoutrements, miners creating the chain. We have a smart contract, and that's really the auction script. So this is the execution of the auction, and it also maintains the state in terms of the contract that's being done. So it interacts both with the edge infrastructure provider and the service provider, and it runs that auction, and makes the state persistent here on the upper right hand side. This here on the blockchain, and then it results in a resource contract as well. And this resource contract is then part of the state that's being persisted on blockchain. So you can get this kind of state. So we should actually go to the other side here because you're recording this. So this is kind of the approach, a very straightforward Ethereum blockchain-based approach. And now the question is, how do you really apply it? And this is the basic mechanism. So what we try to solve is the regional kind of allocation. We have a model from some prior work with Zenith, where we basically divide a space of edge resources into regions depending on their network latency, and we manage it with a point of presence or some base station. And so we're going to use that model here and basically divide all our space into our resources into regions. For each region, we host an auction basically for a particular span of time, and there's one for each basically slot of time that we have. And this looks like that, very kind of an extension to what the picture we saw before. We have we start with contract establishment, and we use a sealed bid double auction on this decentralized blockchain, which is quite nice. So it starts with these interactions. We have our usual participants, the service provider, the edge infrastructure provider. We have a region coordinator, and the region coordinator is an entity that you have to trust less than a real auction house. And then the actual smart contract who performs the auction. And it's being invoked by all the participants with bids, reveal, and then also the determination of the winning bids. This is kind of how it works in a set of phases. You see here it starts with, on the upper hand, with the construction, on the upper part with the construction of the contract, the smart contract for a particular region, for a particular set of time slots. And then there's a next phase is the bidding. So both service providers and service and the infrastructure providers can bid and submit their bids to buy or sell capacity at a certain price. Then the way they bid is they don't make the bids public yet. They submit a hash of the bid in a secret onto the blockchain for non-refutability, but the other participants don't see the bid yet. So in the next phase we have the reveal, where once this is over, everybody's bids are being kind of disclosed in plain text. Then there's a mechanism to determine the winner of the auction. We're going to come to that in a second. It's a McAfee mechanism. And then once you're kind of done, you can withdraw your smart contract claims, and basically as a service provider, go to your infrastructure provider and say, here's, please deliver the capacity that you had promised. So that's kind of the overall flow that this is implemented. And the kind of the cool thing is that you basically use the auction, basically supplement the auctioneer with the smart contract. McAfee mechanism is, don't want to do a mechanism design lecture here, but it's a kind of victory auction where both both buyers and sellers submit bids, and then there's a certain way of how you determine which parts are the winning bids. You basically sort the winning bids sort the seller bids in kind of by price, and the buyer bids in the reverse order, and you match them, and that's how that progresses, and has a number of advantages, I guess. One of the typically 4 desired properties of auctions, of which you can only implement 3 at a time, and the 3 here that the McAfee mechanism provides is truthfulness, so you get the real bids. There's ex post budget balance, means the auctioneer doesn't need to contribute money in any case, and then it supports the individual rationality of the buyer. Now, in the way that works here, it's really this. It supports the utility function that's behind the buyer and seller of capacity. So from a point of view of the service provider, the lower the latency, the higher the utility, right? And the edge infrastructure provider is bounded by the cost to provide that, right? The operating cost, power, and depreciation of the asset. We're just going to skim over this in the interest of time. I guess the McAfee mechanism really is you have these 2 bids, buyers and sellers bids. You order them in ascending and descending order, so you match them in the price, and you find the break-even capacity. That's H is kind of the current index, and you see here that, you know, in this case we have an index, a sell bid of 20 and a buy bid of 40, and that matches, right? The sell bid of 20 and buy bid of 20 matches too, so that you can sell them. But if the seller wants 20 and the buyer only offers 10, that does not. So the 2020, the index of the break-even bid here is 2, and in the right direction here. And then there's the intermediate price you can calculate that represents your cutoff point, and you get to the winning bids. Then in this case it's the one on top, and actually the second one too. And you choose them, and that's your resource contract. And again, you do that for each region, for each time slot you sell off. So it's kind of a lot of auctioning going on. There's an experimental evaluation where we basically simulated selling capacity on a server. This one, we also wanted to have a dynamic component of the cost of the server. So we used national grid electricity pricing as the simulation component as a stand-in for the variability of the price. And then we ran that through Rinkeby as a simulation platform, and show what happened here. And then the 2 results we looked at, on the one hand, was the consumption of gas. Gas is the currency in Ethereum that you use to pay for the execution of smart contracts. And we looked at whether the number of participants or bids really is the determining factor. And in this case, we show that it really mainly depends on the number of bids. That the more bids, the higher the gas costs. And the one entity that really incurs these costs is the coordinator. So bidding is relatively inexpensive in terms of resource consumption on the blockchain, but in particular the determine and the construct is kind of more intensive. So in this case, the coordinator needs to have a fee to recover for the gas being paid. The other one is the evaluation of how good the auction is. So McAfee mechanisms are usually quite effective. As we already saw at the properties, we did some evaluation of the subsidy, which is kind of the price to pay to match winning bids. And typically this is quite an efficient mechanism. So compared to a number of other ones we compared it to. And typically it incurs a very small negative subsidy. So the auctioneer, the auction script makes a little bit of gas, if you like, of money of the auction, and that could be, for example, used to cover the gas that the script consumes. So that's kind of the background of that. So that just shows this is actually a viable mechanism. The one problem is obviously you have a lot of these auctions going on, right? So every region, every zone, there's a lot of different auctions. Also, one of the problems is you have to find the right time slot that's variable, right? It's probably not so much an academic problem or like a market problem. What granularity do you want to buy? Is it like an hour? Is it a day? Is it, and to find the granularity, the more auctions you actually need. And I think this brings me to the end already. Then thank you very much. Thanks.
Thank you, Hiko. This is Lorenzo from University of Messina. So I would like to clarify my understanding about the decentralization of edge. So are you using multiple star topologies deployed on the edge, if understood? And what is the role of the star center? Is this the smart contract coordinator in your architecture?
Yeah, so I think the idea of having so in principle it can the smart contract coordinator could live wherever it lives, but it would correspond to one of the region points of presence to do that. And what was your first question? I forgot that. It's a peer-to-peer topology. It doesn't really need to be star form. And it's not hierarchical. The model does not support, let's say, hierarchical regions. It's just flat.
Hi, Pascal Ho from Loughborough University, UK. Just a quick question about the granularity that you're looking at, because I'm imagining for cloud, if we are bidding for cloud resources, we are looking at like a lot larger chunk of resources for a standard period of time. So I'm imagining because you implement using blockchain, so we know it's limited by the size of transactions it can accommodate. So I'm thinking for edge computing, we're looking at more transient computation, meaning the computation comes and goes really quickly. So what kind of granularity that you are looking at here?
Yeah, I think that's really the open question. So we mainly work with an hour as something reasonable that you could buy. It's probably tricky, and it really depends on the application context. I think for gaming, an hour might be right. For video streaming, maybe as well. But for other applications, you might have bigger chunks that might be viable. See, for automotive, for example, you might. So I think we're going to see that how it evolves in the marketplace, I guess. So I guess we're going to hopefully get some data from 5G operators and see how they do it and how customers buy it. But I'm not yet aware of a public data set of really consumption of edge resources for different use cases. Thank you.
Speaker again. And we're moving on to the second paper in this session. And the paper is on optimized resource allocation on virtualized non-uniform I/O architectures. This is not.
Okay, hello, and thank you for joining me in my presentation today. My name is Tu, and I'm from the IRID Laboratory of University of Toulouse. And today I'll be presenting my work on the optimization of resource allocation for I/O applications running on NUMA architectures. My presentation is going to consist of 3 parts. The presentation of the problem, which is non-uniform I/O access, followed by the description and implementation of our strategy to deal with this problem, and finally some numbers to show how our solution is going to work in practice. Okay, first let's go into the main problem of we're dealing with our work, which is the NUMA affinity of I/O devices versus applications. So as you know, modern servers can have an architecture with multiple CPU sockets. This effectively partitions the machine into multiple nodes we call NUMA nodes. But most I/O devices nowadays, they're only attached to a single NUMA node. That means any application that is running in some node that tries to access an I/O device in another node is going to pay a performance cost. And this cost is going from having to the data having to traverse between the bus that is interconnecting these CPU sockets together, which you can see on figure on the right here. This manifests in not only an increase in latency because you're going through a longer signal path, but it's also an increase in the bandwidth that is being used by the application. So the bandwidth that, for example, the memory bandwidth, data bandwidth is going to be impacted. This is what we call the problem of non-uniform I/O access, or we can call that new IOA for now. So now you would think that it's just a problem of scheduling the correct application on the correct CPU socket, but in fact there are a few problems to that. Especially when you're doing this in a virtual machine environment, when you're running applications in your virtual machine. First of all, virtual machines by default are not configured to be aware of this new IOA topology, you can say that. So they have no idea where the device is attached to, right? So this is, you can blame that on the hypervisors. They don't tell the rest of the topology the machine is using directly. So actually, even if you propose a configuration with new IOA, right? Let's say that you somehow with virtual NUMA, let's say you tell the virtual machines how the NUMA nodes are configured on the real system, right? First of all, the guest is not going to be aware of any changes in the topology, right? If you hot plug some CPUs onto your system, or if you hot plug some memory, the guest will not be aware of this change. And the VMs, the guest, again, even if you give it the virtual NUMA topology, right? The topology of I/O devices are not exposed to the VM either. So this also somewhat applies to the applications that are running on this kind of NUMA topology, because operating systems nowadays, they schedule applications using the information of the CPU and memory topology, but not the I/O topology. So your only remaining choice nowadays is to tune everything manually, to configure everything manually, which is, as you can imagine, it is not only very time consuming, but it's very prone to errors. And it cannot adapt to fast change topology that changes very often. So we made some experiments to study the effects, the extent of these new IO effects on applications that use a lot of IO. We did some networking benchmarks on a machine with 2 NUMA nodes, where we run the application on one node and attach the network card to the other one. We tried several configurations, and we varied the packet size of the data, we varied the rate of sending the packets, we varied the direction that you are sending data or receiving data. So on the right, you can see the figures with the results of our evaluations. The smaller graphs, the 6 smaller graphs on the top are for latency measurements on an Ethernet and an InfiniBand interface. And the bigger ones down here is, I guess, is covered by the thing there, is the latency, the bandwidth measurements. So we found out that by running an application, an IO-heavy application on a NUMA node that is not local to a corresponding device, right? You already have an increase of latency by 6 to 13% when using InfiniBand, depending on your choice of packet rate or packet size. We also tested the same scenario with an Ethernet interface, which is slower than the InfiniBand interface that we tested. And we found out that even with the lower network speed that we are using and a sending interface that has to go through the kernel API, right? So it is, by default, it is less efficient compared to InfiniBand, which the application talks directly to a device, right? Here you still see an observable impact on performance, especially on the latency side. So we did that the same with bandwidth. You see with the two graphs on the bottom, right? Especially InfiniBand, you can observe a very observable reduction in terms of bandwidth, and that is because with InfiniBand or other kernel bypass kinds of solution, for example, if you're using DPDK or if you're let's say using SPDK for your NVMe devices, it is easier to observe this kind of effect because the application spends more time talking to the device versus talking with other applications or with the operating system. And this happens even with our InfiniBand interface that we tested, which is just, if I remember correctly, is 56 bits per second. So, a very early generation kind of interface. So you can imagine that if you have modern devices with, let's say, 100 gigabits, 200, or I think NVIDIA come up with a card with 400 gigabits per second, the problem would become much worse because your data rate is going to go up. Okay, so basically there are two ways of fixing the locality problem of NUMA that are often used. The first is that you try and give the VM one stripe of each node at a time. So you give a little stripe of the first node, second node, third, fourth, and so on. And you look back to the first node. This kind of solution, you call it memory interleaving. It is actually used a lot in physical servers where in older systems where operating systems are not yet aware of this NUMA configuration. But this solution, it doesn't work for all kinds of workloads, especially for I/O workloads. You can see on a figure on the right where the performance of the interleaving solution is very close to the case where there's no locality even. So, or sometimes even worse than that. We also try to configure, to expose virtual NUMA topology to the VM that we are testing. And the virtual NUMA is enough for the VM to process incoming packets. This is because, when you take incoming packets, the interrupts that are going from the device, the signal directly the vCPU of the VM. But it turns out that when you're sending out packets, right, even if you're not scheduled on the correct node, even if you have a vNUMA topology configured, like I explained before, right? The operating system makes decisions not based on CPU, not based on I/O, but based on CPU and memory only. So if you're sending out packets, actually you're making a problem of new I/O worse because the operating system is not making the correct decisions. You are scheduling your CPUs, your programs, applications on a thread that is not corresponding to what you want. So our contribution here is a way to fix the problem of I/O locality for applications. So our idea, basically it has three parts. The first is on the hypervisor, and the basic idea is that you need to give each of the VM a piece of the node that is having the device that it is using. The second part is you need to know which of your applications that is running in the virtual machine in your guest is actually doing I/O, and then you find a way to schedule it so that it makes sense in terms of I/O topology, so it's closest to the device you're using. Okay, for the first part, what we do is, first of all, we need to detect the existing topology of devices, how they're connected to each of the CPU sockets, to the memory modules, and so on. And then you try to correlate it to each of the VMs that you are running. By correlating, what I mean is that we look into the kinds of device that the VM is using. For example, a simple way to do this step is just look into the VMs that are having device pass-through. For example, device pass-through is a very efficient way to do I/O in virtual machines, right? The VMs talk directly to a device rather than having to go through a long, virtualization path. That's a very simple way to do it. A second way is that you can also look into things like CPU performance counters. Look into these counters to see which of your VM is doing the most communication. And after you have done this step, you also need to intervene inside the VM. And what we do here is we see how the virtual topology looks like to know which of the device is connected to which virtual NUMA node. And with the same technique as before, we can try and figure out what are the applications running inside the VM and what of these applications need the most I/O. And we saw above that the kind of kernel bypass solutions get the most impact. So naturally, one of the ways to do this is to detect which applications are doing kernel bypass, which applications are not doing I/O through the operating system, and then we prioritize them. We consider these applications to be a heavy application in terms of I/O. And of course, you can do that also to applications that don't do kernel bypass, so you can have counters that, count how many I/O operations you're doing, and then naturally it becomes an I/O heavy application. And once you have detected all your, let's say, interesting applications, right, you can adjust them so that the applications, they can have a sort of soft preference to the, you can say the home node of the application, right? Let's say the node that it is talking to the most, so that if the application ends up needing more resource, it can, for example, for computing, for other purposes, it can fall back to other nodes without being constrained to just one node. And in our paper, we do have more discussions about our implementation, so you check it out. So after looking at the problem, at the implementation of our strategy, we can have just a bit of a look at our number. We did again the same measurement of packet latency, etc. on InfiniBand using a network benchmark tool from Mellanox called SOPERF. So we compared these numbers to the other configurations that you see above, right? When you have a kind of interleaved configuration, or when you have vNUMA, virtual NUMA enabled, right? We compare them in terms of degradation compared to the ideal case, which is when the application and the I/O device are attached to the same NUMA node. The ratio of difference between performance of these two cases is going to make up the degradation value. And as you have seen in the previous experiments, we see that neither the solutions that are often used, interleaving or virtual NUMA topology, performs very well. And in fact, you can say that the cure here is actually kind of worse than the disease. You can say that. Because the overhead caused by these solutions is actually higher than when you run the application in a remote node in the first place. And virtual NUMA here, it shows the same problem as before, where the VM, it has no idea of where your devices are, so it's not putting the application on the correct node. So we applied the detection and new IOA configuration that we have shown in the previous slide, our strategy there, and we observed that we achieved a performance that is only around 3% worse than the ideal case. Okay, in this slide, we have the same configurations, but we're looking at bandwidth numbers. You observe that, again, the story is exactly the same. Here, you see that both interleaved and vNUMA managed to perform worse than the remote I/O scenario. But when you run the I/O application under our strategy, you mean that you can recover basically the performance back to what it should be, back to when you're running an application like you are running it on its home node. And so again, you have with the two strategies, you have around a 6 to 20% performance impact, right? But with the vNUMA configuration, you have up to the 20 to 30 percent of bandwidth impact on the transmission side, because it's not putting the transmission threads on the correct place, as we have described before, right? But with our strategy, you see that we don't have this problem at all, essentially. Okay, next we are going to look at other types of applications. On the figure on the right, we have two kinds of workloads that we are evaluating. Firstly, we have a storage workload, which we set up essentially a remote disk, and we connect it from our test VM to do our I/O benchmarks over InfiniBand network. And over in this experiment, you see that the remote scenario, right, where the application and the NUMA nodes and the device are different NUMA nodes, it performs worse naturally. You have around 7% of overhead. Then Then next you have the two interleaving, which, sorry, I wrote here UMA for some reason, and version UMA at around 5 to 3%. But again, when you compare that to our solution, which is aware of the new IOA topology, you see that our solution here actually chooses the correct topology for IO process and manages to recover performance. We also did a benchmark of the Memcached database to see the impact of our solution on a more kind of CPU and memory heavy, right? You know, Memcached is in the end is a in-memory database, so it's not going to use too much I/O. So the point of this comparison here is to see that if our solution hurts this kind of application, right? So in this experiment, we ran our database on a test VM that has one of our configuration scenarios that we have listed before again, right? And then we try to load the database with an external agent that run, you can say that's some sort of benchmark on the database, right? Also, again, the connection of the database and the client is over InfiniBand. You can see that from the results on the bottom, right? And that the Memcached database is much more compute intensive, memory intensive workload. It's not doing too much I/O, because when you when you're running on InfiniBand with kernel bypass that we configure for the Memcached database, right? When you compare the remote scenario, right, when the I/O nodes don't match up with the ideal case, you see very little in terms of performance degradation. Oops, sorry. This means that the locality of the device and the application for the case of Memcached, it doesn't actually matter too much. You see that if you apply any of the other strategies, right, the degradation actually gets worse. So here you can get up to 30%, right? Even if you don't have, even if you have version UMA configured, you would expect that because our solution basically it uses version UMA on in the end, right? On the bike, you can say that. You would expect that it will get worse in terms of performance, but in fact, because our workload detection is capable of identifying this application as either IO heavy or not heavy, it means that we actually don't end up making the wrong decisions and that we don't hurt the performance of the database. Okay, so the last, promise the last set of numbers we're going to present here is a small demo of a scenario when you have multiple virtual machines that are consuming different kinds of resources at the same time. Here we have a scenario with, let's say, two VMs. One is running a IO benchmark, and one is running a CPU-heavy benchmark in order to, kind of disturb our IO benchmark a little to see that, okay, if our solution is hurting performance in that case, right? We measure the performance of both of the workloads to see any of them is accidentally degraded. And we observe that even when you increase the number of CPU workers on the second VM that is running the CPU benchmarks, right? The IO benchmark on the first VM is very minimally impacted by less than, let's say, 2%. Sorry, 1%. And that shows that even when you have multiple VMs, right, as long as they're not competing for the same resource, our strategy is not going to hurt it by moving it to unsuitable nodes by accident. Okay, so to wrap up, in this presentation, we demonstrated with numbers the significance of the device locality on the I/O applications. So when you have to put I/O applications on the correct NUMA node, and how this effect will impact your application performance. We show that without manual tuning of the application, the existing solutions do not manage to recover performance, but might actually make the problem even worse. We introduced an allocation strategy that helps to eliminate this, let's say, new IOA attacks, and then we show how it can be applied to several different kinds of applications. You find in our paper more technical details and discussions, and that's it for my presentation. Thank you for listening.
Do we have any questions for the presenter? thanks for pointing out the details in the paper. Can you maybe say a few words about how feasible it would be to move that into a production environment? Do you think that your strategy could be applied to actual data centers?
Totally, and if I remember, this is also one of the points that we discussed in our paper as well. So basically, because our application, right, our strategy, let's say that it doesn't require a lot of modifications on the kernel side of the virtual machine host. So we imagine that it doesn't take too much effort to move this kind of solution to production. It should be very simple.
More questions? Seeing none, then thank you again. And this concludes the session with 5 minutes to go.
Hello? Can you hear me?
Do you want to try sharing your slides? Are you able to hear over Teams if I use this?
Hello, bro. So it works.
Hello.
So can you hear us?
Oh, yes.
Okay. So
Can I start now?
Okay, our first speaker in this session is Jianwei Lin, talking about an efficient adversarial attack on spiking neural networks using spike probabilistic. All right, thank you.
Thank you.
And you can go ahead and start. I can't hear you anymore. Did something change?
Wait.
Oh, that's better.
Sorry.
That's good.
Wait, can you hear me?
Yes.
Oh, okay. Hello, everyone. Thanks a lot for the invitation. My name is Xianwei Lin. Xianwei is my first name, and I study at Fuzhou University in China. I'm very glad to be here to present our work. The paper title is SPA, an efficient adversary attack on spiking neural networks using spike probabilistic. In this paper, we propose attack methods that use spike trains as probabilistic generation adversary sample perturbation, named SPA, which overcomes many shortcomings of traditional adversary attack methods in SM. This page shows the authors who helped me to finish this paper. They are beautiful, handsome, smart young guys. We worked hard together for a long time. Thank you all for your efforts. And then, let us see the context of my presentation. It can be divided into 5 parts. The first section introduces adversary attack technology in spiking neural networks. The second section is background and over-motivation. The third section presents the SPA framework, and then we carried out experiments and compared the result. Finally, we made a conclusion. Firstly, I want to explain what an adversary attack is. Intentionally adding subtle perturbation to the input samples imperceptible to humans, causing the models to give an incorrect output with high confidence. We can see this classic figure when mental perturbation are added to image of panda. The model misclassifies the panda as the gibbon. So, what an adversary attack on the essence? Figure 2 shows IoT device equipped with ether, which output different spike chains through neurons. When the device of these neuromorphic systems are fed with original and adversary samples, respectively, essence remains potentially risky for carefully curved adversary samples. On this page, let's look at the evolution of the neuromorphic neural network. The first generation of neural networks, also known as perceptrons, could not solve linearly indivisible problems, and were powerless of slightly more complex functions, such as heterogeneous operations. The second generation of neural networks, BP neural networks. Although contemporary neural networks have allowed us to achieve breakthrough in many fields, They are biological inaccurate and do not actually mimic the mechanism that operate in biological brain neurons. The third generation of neural networks, spiking neural networks, use models that best fit the mechanism of biological neurons to perform computations that more closely resemble them. Although adversary attacks are a hot topic in deep neural networks, attacks in DNNs may be more appropriate in DNN scenarios than SNNs. We can find why this happens in the difference between DNNs and the SNNs. DNNs usually have a fully connected structure, receive continuous values, and output continuous values. SNNs, on the other hand, use spike signals, which are a series of discrete signals that occur at points in the time rather than continuous values. Therefore, SNNs are not directly available to many of adversary attack methods used in DNNs. Further research on adversary attacks in SNNs becomes necessary. In general, the current adversary attacks in SNNs have the following challenges. First, due to the non-differentiability of the spiking nonlinearity, it's hard to calculate the gradient of the spike chains. Second, gradient disappearance also tends to occur. Third, well-designed perturbations are a vital part of the adversary sample. Fourth, the invisibility of the adversary samples make it impossible for the human eyes to distinguish it from the original sample. So, it's also important to prevent the adversary sample from being identified by the human eyes or built by the model. Fifth, decision boundary finding can improve the efficiency of the attacks and save a lot of costs. Finally, traceability belongs adversary sample to cause attacks in the original model and make the other model predict incorrectly. In order to overcome the above challenges, this paper proposed a perturbation based on the original spike chains as the probability to generate uniform distributed perturbations and construct a new objective functions to generate perturbations that can fool the SN model and make it difficult to distinguish it from the original samples. Our approach also introduced an approximate gradient to optimize the adversary sample generated by the original model for better transferability. The overall architecture of the SPA attacks is shown in figure 3. SPA algorithm first inputs the clean sample X into the spike encoders to generate spike chains. Then inputs the generator spikes into the perturbation generator to generate noise. Next, we combine the noise and the clean sample X to generate the initial adversary sample. This step is repeated for n rounds. The final adversary sample is generated. Finally, feeding the adversary sample into the white box model makes the prediction label different from the original labels. We then apply the SPA attack to both white box and the black box attack scenario. First, we introduce the attack in the white box scenario. Given a clean image and a target model F, the typical task of the attacker is to generate an adversary sample, which satisfies the following two conditions. Two conditions are used to reflect that the attacker misleads the target model to the wrong prediction and to limit the perturbation budget for the attacker, respectively. In practice, the perturbation budget epsilon is usually relatively small, which ensures that the clean image is human imperceptible. Since the loss function of the epsilons are highly nonlinear, direct optimization is complex. We need to convert it into an alternative objective function. So we further reformulate the task of the generate an adversary sample as the following proposals. Here, attackers apply the new loss function as the surrogate for the original attacker objective function. The explicit form of the objective function is as follows. Here, we minimize the objective function. The objective function is composed of two parts. One is the cross entropy loss, and the other is the perturbation, by which the noise and the imageability of the adversary samples are balanced. At this point, we can implement the SPA algorithm. First, the algorithm is initiated, and the input X is poison coded with T as the simulation step to generate the spike trains. The number N of the spikes issued in T obeys the binomial distribution. Second, we generate a sequence of uniform distribution with probability of spikes. All is generated using spike chains as probabilities are more efficient than noise generated as at random. Third, perturbation is generated by a transform function clip, which is added to the adversary samples of T-1 iteration, thus generating the sample of T iteration. Theta is also the helpful yet straightforward tactic used to adjust the convergence rate of the iteration. Kappa is used to store the perturbation generated by each iteration, and the function limits the perturbation value range 0 to 1. Eventually, the SPA algorithm returns an adversary sample and perform an update of the generative model. We also analyze the complex of the algorithm, which can evaluate where F the maximal number of the iteration of the algorithm N runs for selecting p-spike chains. Thus, we can gain the average time complexity. In a black box environment, the attacker has no knowledge of the model's trainable parameters, and thus produce weak perturbations. Our strategy is to use the request for attacks, the output of the black box model is used to optimize the update the white box alternative model. The black box attacks is described as follows. Equation 8 is used here to optimize the gradient of the target model, where G target is the gradient of the target model and can be optimized using adversary sample at moments t minus 1 and t. The equation 9 is used to apply the gradient direction of the alternative model, and this equation achieves the gradient of the alternative model and the target models. In this experiment, the SPA algorithm is evaluated on the static M-list, CIFAR10, Neuromorphic M-list, and CIFAR10 DVS datasets. The most common benchmark datasets within the static and neuromorphic communication, the network parameters and prediction accuracy of various spiky neural networks are shown in Table 1. To demonstrate the performance of the SPA algorithm in a white box scenario, we compare the accuracy of the trainable model within clean samples and adversary samples, and define delta D as the difference between the model's accuracy of the clean image and the adversary sample. Table 2 shows the state of the ANT and SPA performance at the spike and low spike datasets. From the Table 2, one can find that average attack success rate of the SPA is highly competitive. Next, the process of the SPA algorithm to generate adversary sample is demonstrated in Figure 4. The SPA algorithm inputs the original samples into the adversary sample generator and then optimizes them. Finally, it inputs the adversary samples to the discriminator to determine whether the prediction fails, and outputs them if the attack is successful. During the execution of the SPA algorithm, the gap between the adversary sample and the original sample keeps decreasing, and we can see that after 40 iterations, the generated adversary sample is hardly distinguishable from the original samples. By observing Figure 5, the value of the L0 keeps decreasing during the 50 iteration of optimization. In other words, this means that the invisibility of the generated adversary sample is better. In addition, we also show the performance of the SPA algorithm in a in a black box scenario, specifically for a given source model, our approach indirectly attacks other models by the white box surrogate model and the target model on the black box setting. Figure 6 shows the flow of the SPA algorithm under black box attack. The SIFA 10 image is fed into the substitutable model to generate an adversary sample, which is used to attack the black box model. And then a loss function is computed to update the gradient direction of the substitution model, and the results are shown in table 3. The SPA attacks also perform well in a black box setting. We further analyze the process of the SPA attacks. Figure 7 shows the graph of the voltage variations and the spike changes for original number 1 in the white box model under the white box and the black box attack respectively. Comparing the spikes of the clean samples with adversary sample generated by the alternative model, we can find that the spike sequence of the adversary sample are strategized after the disturbance is added, making its sequence different from the original spike sequence. Moreover, a series of ablation experiments are conducted to study the hyperparameter eta and the types of the noise. Different distribution of the perturbation will produce different attack effectives. In figure 8, can see that perturbation values of the normal distribution are small than the uniform distribution as a whole. Still, the perturbation of the uniform distribution is not better for the models. So we select the normal uniform distribution. In figure 9, the loss of the adversary sample and the original sample keeps decreasing as the values of eta increases. In the it has faster convergence when eta is set to a large value. However, as we can see from the graph, the larger value, the initial loss, we aim to balance the convergence speed of the loss function and the size of the loss values. Finally, let's make a conclusion. In this paper, a new technique, SPA, is proposed to attack the essence, which for the first time use Gaussian coding to generate spikes as probabilities and generate uniform distributed perturbation. A new objective function is constructed for middle perturbations and keeping attack success, which is speed up the convergence by adjusting parameters. Experiment results shows that the proposed model can achieve comparable performance to the state-of-the-art works. My presentation is stopped here. Thank you for your listening.
Does anyone have any questions? If you're online, you can put questions in the chat. Any questions in there? Can you tell us about when spiking neural networks are advantageous? I know you talked about that a little bit, but could you talk more about it?
Sorry, I can't.
Is it hard to hear?
Oh, yes.
Can you talk more about when spiking neural networks are advantageous?
Spike change ，spike change 意思的那个sorry, you can pardon. My although English is poor.
You said for images?
Spike change we have made further progress in the study of the security of the spike chains. Now we have in the future we have two plans. One is the further investigate the security risk posed by spike chains, and others is post a defense model in essence.
Okay, thank you. Does anyone have any more questions? Okay, let's thank the speaker again.
Thank you.
Our next speaker is Penny Liu, talking about agent-based framework for autonomic management and supervision of ML workflows in Kubernetes clusters.
Thank you. Thank you everyone to come here join my talk. Hopefully after my talk I could receive some feedback from you experts. Today I'm Penny Liu from Barcelona Supercomputing Center, and this work we collaborate with Lenovo Infrastructure Solution Group. And this work is about the agent-based framework for autonomic management and supervision for machine learning workflows in Kubernetes clusters. I'll introduce some background and then introduce the architecture for our autonomic machine learning workflows. and then show some designs of our agents. And also I will show a lot of like case studies to explain how we use the agent to do the autonomic for the machine learning workflows. I think machine learning workflows compromising some reproducible steps and run as a pipeline to support to enable the machine learning lifecycle. And there are a lot of teams join this kind of life cycle, especially the data science team and the data engineer team. And the data science team, they all face some challenges when they use the machine learning workflows. For example, the data science team, they need to enable the training workflows, and they require some automate in the training steps. And also the data engineer team, after the model is being trained, they need to deploy the model, and also they need to operate the model while the model being deployed in the cloud. Also, they need to take care of the quality of the service of the model serving services. But we discovered, and we think that most of the data science team, they can find some tools that to help them to enable the automate machine learning. For example, I know there are people here, they use the Kubeflow, so it's really nice. So they could use that to automate their training steps, and also they could automate the algorithm selection, the model selection, and something. But this work, we're focusing on helping the data engineer team. Because once the model has been deployed, the data engineer team need to focus on the model robustness, which means that they need to make keep the model accuracy somehow. And also they need to like focus on like maintain the quality of the service. And there are some related work in this area. As I said, the automate machine learning is nice, but the autonomous machine learning, they also exist some tools to help us to deploy. And also there are some tools to help us to detect the problem. But the limitation for those works is they don't offer like different type of inference workflows. For example, now I know that the CLM or the KF serving, they just deploy the workflows as a service. But in any case, the user may also need the batch inference somehow. And also, even there are some tools can detect the robustness problem, but they don't make the autonomous actions. So you have the problem, but you cannot like automate to figure out this. And also, I see the reliability, scalability problem, or the load balancing problem, somehow it still rely on the Kubernetes. You cannot like, yeah, you can have some enhancement in Kubernetes, but it's now somehow like the native Kubernetes. So our main objective is to enable the autonomy to manage and supervise the machine learning workflows to meet some dynamic changes that the service will face in the cloud. So the innovation part, first we have like multiple type of model serving, not only support the model to be deployed as a service, but also the batch inference workflows. And also we enable the multi-layer control, because we see that the changes are from different layers, the user layers, and also some from the infrastructure layer. So we enable multi-layered control. So the agent-based framework, we can enable the agents at application layer to help the model to be robustness. And in the infrastructure layer, by collaborating with the orchestrator, here we use Kubernetes, we can reason in the performance problem. So as I mentioned, there are some changes, dynamic change. They mainly from the the functional, non-functional requirement from the user, and also the internal context. For example, if the workflow executor somehow failed to execute and it's not outside from its internal bug, then the Kubernetes cannot to figure out that, right? So it's somehow related with inside the application. So yes, and then we enable the multi-layer control here. So then let's directly to explain the platform. So this platform, we enable the agents as the scan flow layer in the, is there any laser? Okay, sorry. Oh, here, yes. In the scan flow. And this scan flow layer is the application layer. We enable multiple agents to maintain the application layer knowledge, and also the Kubernetes as an infrastructure layer resource manager. So I can explain a little case here. For example, the user, they just need to submit their workflows to the ScanFlow API server, and the ScanFlow server will help the workflow will append some knowledge within the workflows, and then let it to be deployed in Kubernetes. And while the workflow running as a container in Kubernetes, our agents could do different things regarding the autonomic strategies. For example, the tracker can track the application information and also the infrastructure layer information and save it to the ScanFlow knowledge base. And then the checker could check if there are any anomalies here, and they could detect the problem and tell the planner. So the planner contains some real actions strategies. So it can say that, okay, then we retrain the model, or okay, we redirect the traffic of the model. And then the executor will do the actions to tell the ScanFlow or tell the Kubernetes to do some changes. So this is somehow our agents. Our agents is computational unit, independent computational unit, which contains the which has the mapping from the states to the actions. So which means that once the agents receive the states change, the agents will make actions. And also we defined the autonomic management strategies. The within the strategy, this is somehow define the scenario of the autonomic you want to enable in this system. So it has the events and the constraint and the action. So which means that once the event happens, if the constraint is okay, and then you will do the actions. So every data engineer need to like implement somehow the strategies inside the agents in order to let the agent work. As we see in our system, we are not only just have one agent, but multiple agents. So the agents need to communicate. So there are two ways in our system to let the agent communicate. One is through the RESTful API, but also they could interact through the shared artifacts. For example, our knowledge base. So there are some informations there, so the agent can use. And then we know that the agents need some events and to do some actions. So we predefined some triggers and the operation primitives for the agents. So for the triggers, the agent can have two types of the triggers. One is the scheduled triggers, which means that the trigger will be scheduled every like 1 hour or several minutes in order to sense the state change. Also, the agents can be triggered by other agents. And also the primitives, we also follow the multi-layer control because we have the application layer, infrastructure layer, and for different type of the workflows. So we defined like different operation primitives, then the people can easily use and adapt those. Okay, then I will show some use cases, and then we know how to use our ScanFlow Kubernetes, and also we show the efficiency of our agents. The first example I want to introduce is the minister classification. It was an easy example in machine learning world, but here I want to use this to explain how the different teams can use our platform to collaborate and to deploy their workflows. And also, I will use this example to explain how the agents at the application layer could detect and handle the drift anomalies. And also the second one is MLPerf inference benchmark. I choose the ResNet and to predict the image nets. So with this, I deployed the model as a service. So we can show that how the agents collaborate with Kubernetes in order to figure out some like the context change or non-function requirement change problems. So the first, I show how the different teams work in these problems. So this is the data science and this is the data engineer. So the data science team can easily use the Jupyter notebook and directly use our library, and then you can define the data science to define your training workflows. And you can call like directly the ScanFlow deployment. So the ScanFlow will help you to deploy these workflows in your specific environment. Here is the namespace inside the Kubernetes. So at the end, we will end up with some models like in different version, and also this model registration will like save all the information that you need. And yes, as I said, this part will be easy, but we have the data engineer. So if the data engineer want to like use the agent to manage their workflows, the first they need to define the real scenario, like the autonomic strategies. So for example, here the data engineer use just a Python code to define like the strategies for different agents. For example, we will talk about the drift anomaly. So the tracker agent here just track all the prediction data and save the prediction data in the knowledge base. And the checker will check the anomaly within the prediction data and to pick the important data and append to the new data. And then the planner can use those important data to retrain the model. And this one was to retrain the model. And the next strategy is to upgrade the model, because if the new model has the better like accuracy than the previous one, then the planner can help it directly upgrade the model. And then the executor is the same, because it's not the same, because the planner will see that if the model need to be upgraded, and the executor will do the final action to tell Kubernetes to upgrade the model. Similar as the data science team, the data engineer also need to deploy the workflows, right? So they also can use the Jupyter notebook and our library and to deploy the workflows in Bash or as an online service. So once the workflows run here and the agents could collaborate, could get the information from those workflows, and then it can work. This was the example like we use the agent to deal with the drift anomaly. So you can see like here we have like 4 agents like collaborate to detect the to find the predictions and find anomalies, pick the data, and to retrain the model. So the tracker is to track the predictions. For example, in one agent's running period, the tracker will like count all the predictions. And then the checker here, it will check how many anomalies happens during this period. And then it will pick the important data within this data set. And then the executor and the planner will retrain the model by using this important data. And then the executor will upgrade the model into another version. So this was one iteration. And then you can see here, then we can improve the model from, yes, somehow 90 to 93. This was one. And for the second, as I said, then I used the resonant model, and the data engineer team used the Jupyter Notebook to deploy this as an online service. And also they define the planner and the executor agents. So we use the load gene within this benchmark to simulate the user invocation. So the user are sending the predictions to the online workflows. So we will talk about 3 scenarios. The first one is to compare the agent-based method with the native Kubernetes, because as I said before, you cannot like really consider the user requirement in this case. So in Kubernetes, maybe you decide like, okay, then if we use a CPU at 8 or 5 or 10, then you use scar. But here you can see that if you scar too fast, then you waste the resource. But if you define the threshold very low, then you don't have any scalability here. But to use the agents, you can directly define like because the user requires like the average queries per replica no more than 20. So you can directly decide here this as the threshold. So it's easy to for the Kubernetes to decide if it's it's better to scar or scar up or scar down. And the second one is we also enable some knowledge inside the agents in order to turn the affinity between different applications. For example, here we collocate the online inference service and the batch inference service. But as a knowledge, we know that these two are CPU intensive, then we don't want them to be deployed together in one node. So we can use the agents to enable the anti-affinity among those two applications. So with the anti-affinity, then we see that the throughput is higher. And the last one, we enable the agent to deal with the service availability problem. So as I said that in Kubernetes, the service is available, but you need to restart, but it's the same application. But in this case, we could let the agent to know where is this service's backup service. So as shown in here, this application, yeah, this service works fine, but when the invocation comes, the replica, the service becomes unavailable, and you cannot just restart it because there's a bug inside. But the agent has knowledge that it knows like where is its backup service, so they could redirecting the traffic from the old service to the new service. So this model serving will be fine. So the takeaway here is that the agents could improve the knowledge of the infrastructure layer. So if you provide more knowledge, and then they could behave better. So as a conclusion, we provide the scan flow Kubernetes to enable the autonomy to manage and supervise the machine learning workflows. And we could let different teams use our tools. So it's nice to be used by the data science team, but especially for the data engineer team. And the multi-agent could collaborate and to debug and to find the problem and retrain and upgrade. And the agent also could perform some actions to keep the performance of the service. But for future work, then we could generate more complex strategies inside the agents in order to like make it more intelligent. And also some complex policies could be enabled at both application and the infrastructure layer. Thank you so much. And this project is online now. It's in the GitHub repository. So it contains a lot of examples and also the tutorials and the theory information you can find in the paper, but more practical things and the examples you can find directly inside this repository. We hope that everyone, if you are interested, you can have a try. And then if you have any question, you can contact. Yeah. So thank you.
Does anyone have any questions? You want to come up and take it?
Okay. Now we run the Kubernetes on the 10 nodes, like the real parameter nodes, so in that dedicated cluster. Yeah, thank you. I think so, yes, because the basic one is the Kubernetes. And if you enable the Kubernetes in the edge, which means that you can deploy more services, right? The scan flow, we also deploy this as a service, as well as the agents are service. So if you want to use the agents or the scan flow, you just deploy this as an agent. And this was containerized, so you can directly run this on Kubernetes. Yes, 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 yes. Thank you. Yes.
Thank you again. Okay, our next speaker is Brian Van Esten, speaking about parallelizing graph neural networks via matrix compaction for edge conditioned networks.
Thank you very much. So it's my great privilege to be here today to present this work. This is the work of a fantastic team, both at the University of Binghamton or Binghamton University, as well as Lawrence Livermore National Lab. The lead author, Shatab Zaman, is a summer student at Lawrence Livermore, but also a PhD candidate at Binghamton. And unfortunately, he's not able to travel to the conference this week, but he is online. So if I say anything wrong, he'll jump in and violently object on chat, but you can also interact with him there to ask him any further questions about this. So one of the big challenges we see is that graph neural networks are a very powerful approach for using machine learning on a large number of data sets, particularly those that can be represented as a graph. And a graph is a very flexible structure. So the question is, why don't we see more of these? And one of the challenges is that training these graph neural networks is extremely computationally intensive, and the frameworks that do this are not as robust as they are for sort of visual networks or natural language processing networks. So there's an opportunity to train these models faster to allow us to develop new models, more of them, and on larger data sets. And it turns out that many of these data sets can contain millions to billions of samples, and so the ability to process samples efficiently becomes really, really critical. And we're going to focus, I'm going to show you a little bit later, we're going to focus on one class of graphs, which are small graphs where you have lots of them, but they're fairly, they're really related to sort of molecular and atomistic problems versus, say, large social graphs. And I'll tell you why. We're proposing, we have developed an optimized two-dimensional scatter-gather implementation for training graph neural networks that really allow us to exploit distributed memory algorithms where we use data parallelism across multiple GPUs, scaling up to hundreds of GPUs. We are really leveraging the efficient compute kernels that NVIDIA and AMD and Intel have been implementing in their libraries such as cuDNN, ROCm, and 1DNN. And we really want to focus on balancing our compute load to avoid load imbalance from rank to rank of a distributed algorithm. And we do this by reducing both computation and communication overheads, and again, trading off a little bit of wasted computation for good data layout and reliable and robust communication. We're going to show you that our approach gets good, strong scaling, a parallel efficiency of 75%, where we can get a 12x on 16 GPUs for a single size problem, so that's strong scaling. We can go very efficiently up to 100 GPUs, where we have a 90x weak scaling speed up, and we are about 1.7 to 1.3 times faster than the state-of-the-art approaches in PyTorch Geometric, which is one of the leading competitive toolkits, and we'll show you why. Okay, so going beyond grids. Wow, there's a latency there. All right, so a lot of deep learning has been really focused on sort of Euclidean domain problems. A lot of work's been done for visual problems, and they've really not dug into the unstructured natures of graphs as much as they could, because it's hard and it's hard to do efficiently. But there are a lot of reasons to do it. Bioinformatics, chemistry, quantum chemistry, social networks, knowledge graphs, all of these have important problems that we want to develop new models for. And so we want to, do this at larger scale. We want to be able to train large scale networks. So not just large problems, not large data sets, but also we want the networks to be able to scale up. So we need a computationally efficient framework to be able to do this. And there's really, again, large graphs where you have millions to billions of vertices and billions to trillions of edges. Particularly social networks are one of those things. Reddit is an example of that, Twitter, but also large data sets where you have many, many small graphs. So if you think about like this example here with proteins over there, these things don't have, a billion nodes in a single graph, but they do have, 680 billion possible small graphs. So we're focusing on this small graph size. Okay, so when you go from grids to graphs, what you really want to think about is that a graph convolutional filter is really a generalization of a traditional convolutional neural network, except you can have more arbitrary connectivity between the graph vertex nodes. And that information in those connections is what we really want to exploit with graph neural networks. So you basically set this up as a set of matrices that will capture your node and edge information, as well as the connectivity between those nodes and edges. And what we really want to do is leverage good old linear algebra. We want to really get into the batch general matrix multiply that we love and do so well on our GPUs, and not try to be in the sparse linear algebra regime, because our GPUs still don't do those as efficiently as possible. We're really looking at message passing networks, where you have this formulation here where you have a couple of learnable functions, G and F, which are the functions that you're learning. You have a permutation and variant transformation H, and you're going to learn how these messages get passed between the nodes. Just giving you a little example with H2O here, we see that our oxygen has 2 red features on its node. There are 3 edges, each of which has its own edge feature shown in green. And then, of course, you have your adjacency or your connectivity matrix shown over in orange there. And we're going to compose those structures to be able to do our learning. As I said, there's a wide range of opportunities where we can apply this, quantum chemistry being one of the biggest ones. Protein-protein interaction and drug design discovery are some of these that really motivate massive numbers of fairly small graphs, versus the middle ones where we're looking at, hey, very large data sets or very large graph structures. And not that those aren't valuable, but that's not where we're focusing this work. That's probably Shatab's next paper, hopefully. But you can sort of see here, if you want to think about a knowledge graph and what it means to be a rich, metadata-rich graph there, all your edges have of information on it. And the task we're going to do with message passing networks is we're going to construct a graph, represent it in a algebraically friendly form. We're going to develop and pass these messages logically. That does not necessarily actually imply the communication. And then we're going to update the nodes with dynamic information. So as I said, there's really 2 classes here. We're focusing on graph level tasks. We have lots of small graphs. You hopefully have some labels or targets. You can do a lot of work with unstructured or unsupervised learning algorithms as well. But the task really is often you want to predict some sort of label. And examples are sort of these molecular graphs and what their energy is, or the type of associations you get between pairs of proteins. The alternative, and again, not the focus of this work, is very, very large graphs. Think Reddit, think Twitter, where you might want to do, authorship attribution, role discovery, all sorts of things. But you're really thinking about other tasks such as graph colorings. But here you have a large, massively connected graph, which is its own challenge in how you want to parallelize that training. So when you think about how we're going to embed this problem into a trainable form, we have a set of vertex features. So for every vertex, we have a set of n vertices. There are some number of features per vertex. You have a set of E edges where you have L features per edge, and then you have a basic coordinate list, which is a source sync pair that tell you how they're mapped up. So really, you want these to be regular size structures so that you actually don't have to do memory allocation every mini batch. You can have very structured decompositions across space for multiple compute ranks, multiple GPUs. And the current state of the practice approach does not exploit this as well as we'll show you how we. Is for each vertex, for each neighbor that it's attached to, given. We're then going to aggregate those messages for each vertex, and we're going to update the vertices state for each step. So that's the calculation that we need to do. Oh, wrong direction. I apologize. Okay, so what does the state of the practice do? Well, we have all these little graphs, all different sizes, different number of nodes, different number of vertices, different number of edges, different number of properties per edge. So let's make a single large, massive mini batch of one sample, but really just compact it. So you take all your different graphs, you coalesce that into a large structure, and then you feed that into PyTorch geometric, and it is now, you can sort of pack this to be a reasonable size to get good efficiency out of your GPU. it's really good for a single GPU. The problem is when you want to distribute this over multiple GPUs, each set of graphs that you aggregate may be different sizes, which means there's different work per GPU, which leads to massive load imbalance, which we'll come back to later. You also have dynamically sized tensors, so each time you construct this, you have a different shape that you're going to send into your GPU, so your kernel dispatch is not quite as clean. And again, you have to do all this coalescing for every data structure, your nodes, your edges, and your connectivity. So it's not free. So what do we want to do? We have GPUs that do great on regular shaped tensors, shaped matrices. So we're going to pack it and we're going to pad. So the idea is we have 4 different graphs here, one of which is slightly larger. So we're going to pad all the smaller ones out to the largest size. And you say, well, hey, wait, we're wasting computation. Absolutely. We're throwing away a little bit. But those GPUs are so well provisioned for regular structures that it's frequently better to waste a little bit of computation per sample than to sort of, try and get the maximum amount of computation, but with a very low regularity in how you dispatch. So we're going to pad all of our features and connectivity graph. That really allows us to do regular memory calculation. It also allows us to parallelize it. So if you have 4 or 512, you can give the same amount of work to each GPU in your data parallel implementation, and they're all going to run efficiently. I will note that there is a use case we're going to show where we really stress ourselves, and we have a workaround for this, and we also have some future work that addresses this slightly better. So where did we do this work? So we did this work in a toolkit called the Livermore Big Artificial Neural Network Toolkit, LBAN, proof that I should never be able to name things or make acronyms. But this is a optimized distributed memory algorithm that is from the ground up designed to be able to compose multiple types of parallelism, so model data ensemble parallelism. It has a PyTorch-ish like front end, and you can export, import models between PyTorch, but it really is a C++ MPI code that then leverages the alphabet soup of different accelerator libraries we have at the national labs, and it's designed to run on the top, leadership class computings. So this toolkit has run on all of Sierra, all of Fugaku, systems like that, and it's open source, and it's shown there where it's on GitHub. But the idea is that by packing our data structures into these nice regular size things, we can actually get a very regular computation. So what we see is we now have our node and node features here, our target industries. This is going to turn into a gather, apply, scatter, out implementation for the whole message passing framework. And the communication across ranks is really in the gather and the scatter. Gather and scatter, not scather, scatter. And so the idea here is that we're going to basically use a MPI collective or nickel or rickle, and we're going to gather all the features into, so again, regular size structures. We're going to push that into GPUs. We're going to then be able to do a scatter at the far end to be able to distribute it. And this is actually going to be much, much more efficient when we go into our batch GEM algorithms where you want all of your time to be anyway. So this has been pretty cool. So where are we going to use this? So for this example, we have used this on we're going to use this for representing molecules. And this is a really great example where you're going to have your atomic information stored on each vertex. You're going to have your bond information stored on your graph edges. And what's interesting is that if you look at some of these data sets, they're like 140 million or something, all the way up to like 680 billion possible elements in a data set. So again, the appetite for compute here is essentially unbounded. The challenge is the chemical state space. When you start going to like 17 atom pairs, it just grows exponentially. The state of the art for doing this classically is with density functional theory, and the problem is that these algorithms grow cubically in the number of electrons, and so they can be really, really expensive to train in a classical sense. So if we can develop reasonably good surrogate models, we might have an opportunity to couple that with our traditional scientific simulation. So we are working on molecular property prediction using the Open Graph Benchmark PCQM4M, rolls right off the tongue. The idea here is that we have 3.3 million samples. The average degree of each sample is 2.5, so you can see the stats there on how big. So again, small graphs. But again, this simple data set has 3 million. The neural network that we're using is shown here on the right-hand side. This is a standard one in the community, and again, the goal is to predict these DFT calculated quantities. So we're using an edge-conditioned MP-NN architecture. I will say up front, when we trained this with our implementation, we achieved a state-of-the-art accuracy of 0.197, which is comparable with the reference benchmark. The rest of the talk is going to talk about performance, and when I mean performance, I mean time to solution, not improvements in model quality. That is an orthogonal goal, very important, but not the subject of this work. So what do? We took the data set they have. They didn't actually give us the prediction values, so we took our data set, we split it up between test, train, and validate. So that we could actually do some good science on there. And we tested this on 2 systems at Livermore. Pascal is an x86 system with Tesla P100s, and also Ray, which is Power 8, and again, 4 Tesla P100s. So the first result we want to show here is that when we perform strong scaling, the dense scatter algorithm that we implemented in LMAN outperforms the sparse coalesced implementation that you see in PyTorch geometric. So on these graphs, I have the number of GPUs on the x-axis from 0 to 32, the speed up on y-axis relative to their own baseline, but also on the right-hand side, the absolute performance in terms of the time to process a single mini batch between these two. The state of the practice is in orange and our implementation is in blue. And what you can see is, one, we are able to get a much greater speed up going from 1 GPU to 16 because of the regularity and the lack of loss due to kernel imbalance. But also, we show that we're able to get a 1.7x speed up in terms of we are just faster at 16 GPUs. Now, I'll say with this example, the system saturated. There just wasn't enough work to scale it out beyond 16 GPUs because this is a strong scaling problem. So we started with a fixed size mini batch, and as we add more GPUs, each GPU has less work to do. This is not weak scaling. We'll show that in the next plot. So again, doing this well is hard, but when you can do strong scaling well, it's great because you don't have to change your learning algorithm. As most people know, if you weak scale your problem and you increase your mini batch size, you must tweak your learning rate for any reasonable model to get it to learn as efficiently. And actually, many models don't actually learn with large mini batches. So exploiting as much strong scaling as possible is a goal we always have. Okay, let's talk about that large scale training. So in this example, we have the number of GPUs again on the x-axis here, the percent efficiency of our calculation on the y-axis for the left-hand side, and the total runtime on the y-axis for the right-hand side. And what we can again show in blue is that we are able to outperform the PyTorch geometric implementation on the far right-hand side. That's about 1.3x, I believe, there. But more importantly, if you look at our work per GPU, we are able to keep a much higher percent efficiency of those GPUs because of our load balancing. I will say that in this, we didn't tweak the learning rate to be able to make sure that we always achieve the same quality here, but that is an exercise left to the reader. We were really focusing on the strong scale or the weak scaling performance of this. And again, improved time to solution here. This is time to a converged model, going with number of GPUs on the x-axis all the way up to 100 GPUs, and our speed up here. This again is a weak scaling problem again. So this is a converged solution, not necessarily the best solution. Again, tweaking learn rate is important, but not what Shatab was focusing on here. And what we see is that we can get an 89x speed up on 100 GPUs. So not quite linear, but really darn good. So I keep talking about the challenges with the state of the practice approach, and we're trying to show that here whenever this refreshes. There we go. All right, so here we have the GPU utilization on 2 different plots. So time, this is wall clock time as we observe the calculation going on in more or less real time. The GPU utilization reported by the NVIDIA tools. And what we see is that the sparse coalesced implementation has these massive swings in efficiency. This was done on 2 GPUs out of, I can't remember how many were used in this, but it was multiple GPU run, but we are only observing 2 of them. And we see that as we go from mini batch to mini batch with sparse coalescing, the amount of work you have changes dramatically. And so you get these wild oscillations, which causes the whole learning to actually pause as one GPU catches up to the other, because they're doing synchronized stochastic batch gradient descent in a data parallel fashion. This is, on the right-hand side, is our implementation. You can see a much smoother and more consistent utilization of the GPUs, which is one reason we can get, even though we're wasting some amount of work, we get much higher efficiency. Okay, so let's put ourselves to the test here. What are the challenges of this method? And the challenges are, if you have a massively imbalanced graph data set where your average degree, even if your average degree is fairly low, if you have large, especially power law connected graph or nodes where they have like, exponential number, that can break things. And let's show you why. The challenge is that in our current approach, you're going to pick the largest size sample with the most connectivity and pad out to that. And so again, if everybody's pretty similar, molecules that all behave pretty well, that's not too bad. But if you get these very large graphs, this can go badly. And so, again, these heavy tail data sets. And so it turns out that this is not really an issue for chemistry because there's only so many bonds you can have. So this is pushing beyond that. But again, if you looked at like social networks, that'd be a huge issue. We are going to look at a more challenging data set. This is now a protein-protein interaction, and there's 80,000 training samples in here. But what we see is on this graph here, we're looking at just index number of graph samples sorted by their degree of connectivity, where the number of edges they have is on the y-axis. And you see that a lot of the graph is really well behaved, except there's a long, ugly, heavy tail over on the right-hand side. So if we just said, let's pad out to that last one, that orange space on the graph there is all the wasted work we do, which we don't want to do. That would be inefficient. So how do we address this? Well, we truncate, stratify, and progressively train. So the idea is, actually, we're going to stratify, truncate, and progressively train. The idea is we're going to split the data set into multiple sets. So we show here where basically these rectangular blocks are where we identify a reasonable cut in the data set where we keep, I think it's like 89% of the graph in blue there to the left where it has that orange overlay has a close enough average degree. So we take that as one slice of the data set, and we're going to pad it out with this orange level of padding here. Then you're going to do that for that green section, and then on the far right-hand side, it doesn't show up well on the projector. We actually are going to pad out there, and we might actually want to say, what happens if we threw away the most obnoxious parts, examples of this? Well, you're losing information. So again, this is sort of a visual of like how much work we're avoiding by being clever about how we carve up our data set. So now the question is, well, can you do this? The important litmus test is when you carve it up into these chunks, are your split points representative of the entire data set? Because if they weren't, you'd get really imbalanced learning where you train on one chunk of it, but it's not representative of the entire problem. So we looked at the number of classes for this problem, just arbitrarily labeled here 0 to 35. And what we see is what's the distribution in samples if we have the full data set in blue on the left hand for each stacked part of the bar chart. The orange if we took 80%, which is sort of the smallest chunk. And then the green is if we went 80 to 99%. And what we see is that we can basically throw away the 1% worst performers in terms of how their number of degree, and then keep everything else and actually have a nice representative set of data. We also can show that we get a reasonably similar result in terms of quality of the network. We lose about 0.5% in terms of quality of trained model when we do this. And when we do this, what we see here, so here are four plots. So each one is number of GPUs on the x-axis, the runtime on the left-hand cluster. So I have two pairs here. So runtime on the y-axis for the leftmost, and then speed up in terms of performance on the right-hand pairing. And we do this for a small version of the data set and a large version of the data set to really sort of see how challenging this is. And what we see is that initially, this is where PyTorch outperforms us, right? They have a better runtime here because of the imbalance and the excessive padding. We do see that as we get to a large number of GPUs, PyTorch stops scaling and we do better. It's hard to see on this plot, but in terms of total speed up, PyTorch dips over and starts going down in terms of its performance, we actually still get a pretty good speed up all the way out to 32 GPUs. So pretty good, not our best. This is showing our dirty linen. If we go to the larger data set, we see a very similar approach as well, where again, only at the largest number of GPUs do we get improvement over the sparse coalesced version in PyTorch. But again, we are showing much better scaling efficiency as we go. Now, just to start wrapping up, we do have ideas for how to improve our efficiency for heavy-tailed data sets. There's some clever things we can do with combining local batching, sort of like a little bit of the sparse coalescing where we pack them into regular size structures, but we do a little bit of bin packing there to be able to actually avoid some of this problem. And also the next thing we're really looking at is how do you use tensor parallelism to deal with much larger graph sizes and graph problems. All right, just to wrap up, because I am between you and lunch, and I appreciate that you guys don't want to hear me say much more. So the motivation here is that there are many, many scientific problems that can be represented as graphs, but we need to be able to train on these data sets faster and more efficiently. So we have developed new methods for making standard distributed data parallelism work more efficiently using the compute resources that we have. We've demonstrated that by throwing a little bit of compute away, we get much better communication, much better load balancing, and we're able to show that we can get really good hardware acceleration or speed up using this algorithm, both with respect to our own scaling performance for both strong and weak scaling, but also in terms of the state of the practice implementations in PyTorch geometric. And this work is out there and published on GitHub. So really this work has been focusing on graphs with that low average degree and bounded edge sets, which really are representative of both atomistic and molecular and protein-protein interactions. And so that's a very rich class of problems. This is not targeting your large social media graphs. With that, Shatab kindly put in a bunch of references for the work, but I'd like to thank you for listening to me for half an hour. I'll take any questions. The audience has been bludgeoned into submission.
Any questions in the room? People are probably hungry. All right, well, I'll save my questions for later, then we can talk over lunch. And thank you again.